Hello. Good morning, ladies and gentlemen. The galaxy of intellectuals, Your Excellency, invited guests, teachers, and my dear friends. How different is this morning? Indeed, very wonderful, in fact. And I'm Utkarsh Kumar Singh. I'm going to be your host today, this webinar, and I humbly invite you all to this session on Indigenous Li Fi 5G testbed at IIT Delhi in partnership with TSTSI. Before we begin, I'd like to address some protocols regarding this webinar. This webinar is currently being recorded. All participants are requested to keep their cameras off and mic muted. If you have any queries, please write them down in your questions tab provided on your GoToMeetings dashboard. We'll have a question answer session after each talk. Please maintain clarity in your questions. Your questions will be addressed by the session speaker directly. We'll have a networking break mid-session. To know more about the organization, additional handouts are available in Handouts tab on your GoToMeeting dashboard. So let's begin. First, I'd like to invite Professor Huzur Saran, who is Professor in Department of Computer Science and Engineering at IIT Delhi and currently mentoring the project building end-to-end 5G testbeds at IIT Delhi. Dear sir, I request you to please turn on your webcam and inaugurate this session.
Hello, my webcam. Just a minute. I need to allow the webcams in there.
All right, sir.
It's not allowing me to.
It was visible for a second up there, sir. Can you click that button again?
Sorry, I'm not able to open the webcam. I don't know what the reason is.
All right, sir. You can start speaking just like this.
Well, what I will do is, webcam refuses to open for some reason. I don't know. Anyway, I'd like to just share. My slide.
All right, sir. Hold on.
How does one go about sharing the slide?
So I'll make you the presenter. Hold on. So please select your PowerPoint presentation in the prompt it's asked, and you'll be live.
Okay. Can you see my screen now?
Not yet, sir.
Can you see my screen now? There is this thing says share screen. I clicked on it.
Yeah.
Maybe I need to restart your GoToMeeting.
All right, sir. You can restart.
Let me rejoin the call.
If somebody, Utkarsh, if somebody else can present his slide, that would be great.
All right.
Utkarsh, can you invite Professor Bridget Lahr to do his presentation?
Yes. All right. For the time being, I'd like to invite our keynote speaker, Professor Bridget Lahr, who is professor in Department of Electrical Engineering, IIT Delhi. He's in charge of Samsung IoT facility and also a co-mentor of project building end-to-end 5G testbeds at IIT Delhi. So I'd like to invite you here, sir. Please turn on your webcam and unmute yourself.
Here, Utkarsh, am I audible?
Yes, sir. You're audible loud and clear.
And I hope you can see me as well.
Yes.
And let me try and share a slide, which is an indicative slide. I hope I'm able to share that. So no,
Yes,
this is
sir.
not the sharing slide. Where is the, how do I share slide?
So go to your GoToMeetings tab. There's a show applications button. Just click on the drop down menu and select your presentation.
Okay. So this is go to meetings. So for sharing screen, I'll have to quit. So it doesn't matter. I don't need to share the screen. Let me just talk without sharing the screen in that case. All right.
Yes.
So I will continue.
Yes, sir. Please continue.
Yeah. All right. So now, well, this is not much of a keynote. It's a short presentation to gently introduce you to the concept of Li Fi and give you an idea of the kind of work that we are trying to do here for Li Fi. So the idea here was that when this 5G testbed project started, we were looking at 5G and its evolution and its co-working with other technologies which make sense in context of 5G. So Li Fi represents one such technology. What happens is you have lighting all around you, and free space optics and fiber has for long been used as a chosen mechanism for high speed, high bandwidth communication. So what has happened of late is that there has been a realization that light has a good light can act as a good medium for communication as well. So there is this convergence that is happening in lighting and communication industry, which makes a lot of sense, especially in indoors. When you're sitting indoors, the lights or the smart LED bulbs are always on, at least in the evenings, and sometimes in offices even during the day, that you let into your premises. So what has happened because of that is that it is very natural for people to start considering the possibilities of using light as a medium for communicating rather than just lighting the space up for working. So this is the genesis of Li Fi as a technology in general. As far as IIT Delhi or this particular institution is concerned, we have a strong group working in the area of optical communication. We have multiple faculty members who make strong contributions in this space. For this reason, it was only natural that when we came up with this particular project proposal, we include Li Fi as a part of it. So when we went about including Li Fi as a part of it, how do we integrate it with the larger ecosystem of the 5G? So what happens is 5G can get the signal right into if you have to, for example, transmit it within a room, or for example, within a train or a bus, the light could act as a very good medium for that particular communication. So that is the genesis of this particular project. As you will see in expert talks and demos later, we have been continuously improving the capabilities of the system that we are building here. What we are able to do now is get increased capability to communicate between a BTS which could be connected to the 5G system, and the BTS transmitting to devices that are in the vicinity of that particular light. If I had been able to share a slide, I would have shown how this setup is being done, but I think you will see a lot more of that later. But the fundamental idea remains that light, because of the high frequency, has the potential to communicate or to transmit information at a very high speed at a very large bandwidth. So lots and lots of data can be moved around, and what happens is that you when you are in a room, you will probably always be using light. Now, besides indoors, what is happening is that Li-Fi is also finding its way into outdoors. As you know, that the other place where wireless optical communication is gaining ground is in well, short short distance backhaul. If you want point-to-point communication, which is of reasonably high bandwidth and has properties of robustness and reliability, people are using FSO for those short-range links. So FSO was already finding its way there. Now, more recent work is not looking at FSO as the only means for this kind of communication, because in FSO you have a very pointed beam. So you had issues such as pointing errors. And of course, so because of that, the design and the location of the receiver and transmitter, there were quite a lot of design constraints that used to come into picture. So now some degree of scattering, not a very large amount of scattering like it happens in Wi-Fi, but or in wireless or RF based communication, here you do allow some degree of scattering. So so rather than work with very high quality lasers which give you very pointed beams, even in outdoor scenarios where you're trying to or some short haul kind of communication, Li-Fi or VLC kind of communication is also being considered. So this is one aspect. So this is where VLC or Li-Fi found its way into the communication ecosystem, and this is where it is headed. So not only will it be used after the last mile, which is after your RF or the the access loop, where you have the air interface. Even after the air interface, you will use Li-Fi to connect to a lot of devices that you could have in the room. One could be high bandwidth connectivity to your mobile phone or to the laptop, and the other possibility is connecting it to a lot of sensors that you might have in the room, because as we move towards smart campuses, smart houses, smart buildings, the number of sensors that will be deployed in rooms and in locations around you will keep increasing, and all of these can be potentially connected using a Li-Fi kind of a network. So it has application not just in high bandwidth connectivity, but also in large number of concurrent connections, so that a lot of sensors which transmit information in small amounts, but critical information which when put together gives you a lot of information about the environment that you're working in. So both of these applications can be satisfied by setting up a good Li-Fi network indoors. Outdoors, it has potential as well. It could for example be used along with streetlights to provide hotspots at certain locations. Otherwise, it can be also used for communication over short ranges to bump up the backhaul or front haul or mid haul kind of connectivities, which are becoming extremely important, and they require reasonably high data rates to work with. So this is the kind of applications that are slowly evolving from this particular area. The kind of work that happens in this field is people explore modulation techniques, they look at receiver designs, they look at things like increasing the range, increasing the bandwidth that can be supported. So this is the kind of work that continues to happen, while in parallel people explore the possibilities of improving the receiver and transmitter, where you have those LEDs and photo detectors, both of which people are working on. So there's this whole um, bunch of research areas in which people are working, right from devices where you have your transmitters in the form of LEDs and receivers in form of detectors, plus you have modulation schemes to improve the efficiency with which you use the bandwidth that becomes available. You talk about receivers so that it performs better even in relatively difficult channel conditions, and all of this is put together in form of applications which you are so convergent and so natural that they sort of just disappear into the ecosystem around you, and you don't even notice that you have separate communication devices. You do not need separate Wi-Fi routers to make you stay connected. They are just part of the lighting system of the building that you're in. So this is pretty much what I want to talk about at this point in time. I'll hand it back to Professor Saran to inaugurate this, and then we'll hand it over to the experts to tell us a few things about what's happening in this space. Thank you.
Thank you so much, sir, for your kind words. I'd like to invite Professor Saran back. Sir, can you please turn on your
Hello.
webcam? Yes, sir.
Yes.
Hold on a
So can you hear me?
Yes, sir. Loud and clear.
Yes. Okay. You can either put up the slide so that others can see that.
Yes, sir.
Yeah. So yeah. So yeah, if you can make it full screen. Thank you. So
Right.
so as you can see, I just wanted to briefly introduce the 5G testbed project, for which overall, which I'm sure you may have heard of before also. But about 3 years ago, the Department of Telecommunication, the Government of India, decided to fund multiple IITs. As you can see, IIT Bombay, Hyderabad, Madras, Delhi, ISC, IIT Kanpur, and two research and institutions, CVIT, which is in IIT Research Park, and Samir, which is a Ministry of Electronics funded Center for Microwave Research. So all of these institutions collaborated together to try to build a full-fledged 5G test bed. And the funding was up to the order of 200 crores. And the Li Fi project that we're going to talk about today, and which Bridget just introduced, is part of this larger picture. And I should mention here that the Government of India is continuing to support beyond 5G. And only a couple of days ago, we received confirmation from Ministry of Electronics and IT that these 8 institutions and maybe 1 or 2 more now have been sanctioned a follow-up project which is going to look at beyond 5G technologies. So that's just an introduction that of the overall sort of larger activity at IIT Delhi and all the other IITs, and we are collaborating together on many of the areas of 5G beyond just Li Fi and some of the sub areas. We'll briefly, can you go to the next slide, please? So as you know, 5G vision is anytime, anywhere connectivity. If you want to keep a person connected, whether at home, office, or driving, or whatever it is. And as you know, nowadays there are technologies like SpaceLink, where small satellites orbit the Earth at low Earth orbit satellites and give you high-speed connectivity anywhere, even in the remote wilderness. You can get connectivity. Strictly, that is not 5G, but the vision of 5G is to integrate all of these things. Also, there is this need to be able to connect all sorts of Internet of Things devices and do it very efficiently, be very energy efficient. And that is where things like VLC, visual light communication, also come in. VLC, the light communication, is far more energy efficient than radio communication at times. Next slide, please. In 5G radio, there are many new things that have been standardized. There is millimeter wave. There is the ability to have hundreds of antennas and do beamforming, massive MIMO, and many other things. I will not go into all of them here, but device to device and vehicle to infrastructure are also areas. And for example, in device to device and vehicle to vehicle, multiple technologies, including even VLC, could be used, right? So next slide, please. So what is the 5G testbed trying to do? It is trying to, as you know, digital connectivity, and with the pandemic which happened in the last 2 years, this has become even more important. Digital connectivity has become like a lifeblood for the working of all of us, right? Somebody who has nothing to do with IT also cannot get his work done without this kind of anywhere, anytime, high quality digital connectivity. So, and so in that spirit, and with the spirit of Make in India, Atmanirbhar Bharat and all that, so there was a need to ensure that the expertise within India was used to bring India into the key contributors of 5G standard development. And as you know, recently a standard has been approved by the international, the 3GPP, called 5GI, which is an India-specific enhancement of the standard 5G standard. And that has been done through the efforts of many of the same institutions I mentioned here, and of course DSI. So there has been a lot of work in the last 3 years using support from Government of India, including this testbed project, on creating 5G technologies relevant to India, right? And making sure it is also internationally recognized. Next slide, please. And the 5G testbed does not limit itself to only these 8 institutions. We work with Indian and foreign equipment companies. For instance, with Ericsson, we have a 5G testbed at IIT Delhi also, but supported by Ericsson, which has been handled by Professor Bridget. And we have been working with startups in India. We have been working with TSDI, of course, and we have been working with the various operators, including Airtel and Reliance Jio. So it is about developing a whole ecosystem of innovation in this country. Next slide, please. Next slide, we can just, I'll just briefly mention what kind of topics we have been doing in this 5G testbed. Millimeter wave radios for the front end have been developed, and Samir has been leading that effort because of their microwave expert, and of course IIT Madras and IIT Hyderabad. The massive MIMO subsystem up to 256 antennas has been developed. Switched beam array antennas, full duplex radios, functional 5G base station has been developed. We have been working, IIT Delhi has been in the forefront of looking at edge computing as a means to offer very low latency response times to applications for augmented reality, virtual reality, and many other scenarios. Next slide, please. IIT Hyderabad has been working on Cloud RAN. Again, I'm not going to try to explain all these technologies given the time available. I'm sure many of you are familiar and others can easily find out about it. And we will be hosting different parts of the testbed groups. We'll be hosting, along with TSDSI, seminars on many of these topics. Use of software-defined networking and network function virtualization to create the core networking platform, which has been created by IIT Bombay. Professor Swadesh Day, Monica Agarwal, and others from IIT Delhi have been working on using 5G technologies for Internet of Things, including narrowband IoT. And we have deployed narrowband IIT base stations on campus and are doing experimentation on many interesting technologies using that. Professor Harshan Jagdish here at IIT Delhi and I myself and others have been looking at security for the 5G, including security for IoT, security for the core network design. And then today's seminar, led by Professor Abhishek Dikshit, is on the benefits of Li Fi to be able to do device to device and last hop connectivity inside buildings and even outside. And that is about the Li Fi system that you will hear much more of today, which is a very interesting and very innovative system. So with that, I will close and look forward to hearing from Professor Abhishek Dikshit and his team on the very interesting work done in Li Fi and more generally the broad background of Li Fi. Thank you.
Thank you so much for your words, sir. So it's time to begin our expert talk session. So let's get technical. I'd like to invite Professor Abhishek Dikshit, who is Assistant Professor in Department of Electrical Engineering at IIT Delhi, and his area of research includes optical communication, signal processing, and optical wireless networks. He's here to talk about visible light communication, its challenges and solutions. Sir, I request you to please turn on your camera, microphone, and please take over this session.
Hello, thank you, Utkarsh. Utkarsh, how to share the slides?
I'm sending you the prompt, sir.
Okay. Are my slides visible?
Yes, sir, they're visible.
Okay. Okay, let us start. First, I would like to thank Professor Huzur Saran and Professor Brijesh Lal for giving this kind introduction of Li Fi, which I will be talking more about. As Utkarsh has mentioned, I am Professor Abhishek Dikshit. I work in the Department of Electrical Engineering. So let us start the presentation. So first, I will introduce what is Li Fi. Then we will talk about Vlc system model. Then I will talk about multipath channel modeling and characterization, typical modulation schemes that can be used in VLC, typical multiplexing techniques which can be used in VLC, and then I will also show some demos of the work here at IIT Delhi. So let us start the presentation by introducing to Li Fi. What is this Li Fi? Let's try to understand this. Li Fi is a light communication system which transmits data at high speed. Okay. So typically it can use visible light, which is between 400 terahertz to 800 terahertz. It can use ultraviolet, which is between 800 terahertz to 30 petahertz, or it can use infrared spectrum, right, which is in this frequency range. So Li Fi, in essence, can use either infrared or visible light or ultraviolet. At present, the most favorable solution is to use visible light or visible range. And the main reason is so that illumination can coexist with data transmission. And the most preferred solution as of now is to use LED lamps as the transmitter. Okay. So if I look at the Li Fi, as I've mentioned, it can use ultraviolet. KAIST University is doing a lot of work on ultraviolet Li Fi transmission links. In visible light, IIT Delhi is doing its work. For infrared, ISC Bangalore is working. So typically, if you have to look at a particular flavor of Li Fi, you have to look at the research papers from these institutes. So as I have mentioned, we are particularly looking at visible light communication as a potential candidate of a Li Fi link. What is visible light communication? It's a short range optical wireless communication technology. It operates in the visible range 400 terahertz to 800 terahertz. It uses LED lighting, and the main reason, as I mentioned, is to provide both illumination and communication. That's the key of using visible light communication. Now, as I mentioned, whenever we are talking about visible light communication, normally 95% of the time it means using light emitting diodes as the transmitter, right? The same light emitting diodes that you see at your home, in offices, and so on and so forth. So the first question that we have is, why should we use LEDs? That is what we have to understand. And if we want to look at luminous efficacy of various sources, luminous efficacy means how much lightning a source can produce. Lightning is measured in terms of lumens per watt, right? So every source requires some electrical power per watt. How much lumens a source can produce, that is what is luminous efficacy. If I look at luminous efficacy of various sources, you can see incandescent light source has a typical luminous efficacy of 16. We have improved it by using fluorescent sources to 70, but LED has a luminous efficacy of 300. That means per watt it produces a lot of light. As simple as this, and thus it's very energy efficient source. Not only in terms of luminous efficacy, but also in terms of lifetime. That means for how long a device on average can work without failure, that is also very high for LEDs, right? You can see these numbers here. Thus LEDs have both a very high luminous efficacy and a very high lifetime, and thus it's but natural to use LED as a transmitter. And this also we can see from this slide, where you see that if I look at the brown arrows, we can typically see that the percentage of LEDs that will be produced is increasing continuously, and by in years to come, at least it will be the most dominant lightning source that we will have on this planet. And the reason, as I've mentioned, is because of high luminous efficacy and a high lifetime. Now, when I'm saying LEDs, there can be different types of LEDs. We can have phosphor coated LEDs. We can have red, green, and blue LEDs. We can have micro LEDs. We can have organic LEDs. Typically, micro LEDs and organic LEDs are used for display, and phosphor coated LEDs and RGB LEDs are used for communication. And one primary reason is because it has good efficacy, luminous efficacy, and it also has a reasonable bandwidth of around 5 megahertz in phosphor coated LEDs and about 20 megahertz in red, green, blue LEDs. Okay, and these numbers in some other research papers are even higher. So for red, green, blue LEDs, people claim up to 100 megahertz. These are typical numbers. Okay, so as I've mentioned, phosphor coated LEDs and red, green, blue LEDs are typically used for communication, and these two LEDs are used for display purposes. And in this work, we will be focusing on phosphor coated LEDs. Okay, we will not be using red, green, blue LEDs, and the primary reason is that it is more complex to use red, green, blue LEDs, because at all times we want to maintain white light, right? And using red, green, blue LEDs make this complicated for us. Okay, so for the work at IIT Delhi, we're just looking at phosphor coated LEDs. Now let us try to understand how can we get more modulation bandwidth, or how can we get more bandwidth on these phosphor coated LEDs, and this is a very toy model of what happens in a phosphor coated LED. Blue light hit phosphor, and this produces phosphorescence, which results in yellow light. Yellow light mixes with blue light to produce what is known as a white light. And this process, phosphorescence, is very slow process. Okay, so this basically slows down my device. So the idea to make these LEDs fast is just to use a blue filter. Blue filter stops this yellow light at the receiver and passes only blue light, right? So just by having a blue filter, you can get rid of the disadvantages of a phosphor coated LED, right? And the main disadvantage was low bandwidth. So using a blue filter at your receiver, you can push the modulation bandwidths of your phosphor coated LEDs. Okay, so we are using this solution in our work. We are using phosphor coated LEDs, and at receiver we are using blue filter. As I mentioned, it can kill effect of slow phosphorescence, and it can give or impart a very high bandwidth, typically of 100 megahertz. It's still not very high, it's not in gigahertz, but yeah, this is what we have to live with. 100 megahertz is reasonable. So we have understood visible light communication is one potential solution for Li Fi, and we are looking at light emitting diodes because of higher reliability and energy efficiency. And we are using phosphor coated LEDs with blue filters, which is a good option to get hundreds of megabits per second. So why visible light communication? That's some other question that pops in head of everyone who first looks at this VLC or Li Fi. The first primary reason is RF spectrum is a regulated spectrum. You have to pay for it, right? There is also a capacity crunch in RF spectrum. This VLC has very low electromagnetic interference. It has very good security. Why it is secure? Because light doesn't penetrate outside your room. So whatever you talk stays in your room. You cannot have eavesdropper penetrating into your communication system. And because light stays inside a room, this also gives us an opportunity to do spatial reuse. That means in one room, I can use one LED transmitter and receiver. Another room, I can have completely independent LED transmitter and receiver. These two doesn't interfere. It's safe. Human bodies have been exposed to light for, I don't know, billions or millions of years. And so far, there has not been any report of cancers or deadly diseases because of use of light. Is energy efficient? I have already mentioned. And this can be integrated with existing lightning infrastructure. That's the key thing. You do not have to rebuild your lightning infrastructure. It's already there. Transmitters are already there. You just have to use it. So applications of VLC we can use for indoor wireless communication, which is the primary thing for which we are using VLC at IIT Delhi. It can be a secure solution. You can do Wi-Fi data offloading. You can use it for energy harvesting. You can use it for RF interference sensitive places. You can use this for indoor positioning. We have done some work also here. You can use it for alert system, underwater communication, so on and so forth. So there are a lot of applications of VLC. Okay, so I have introduced what is Li Fi and what is VLC, and for the remaining of the slides, I will only be focusing on VLC. Okay, and the first thing is we have to talk about the VLC system model. So if I look at the LED characteristics, so it produces luminous flux or light or power or intensity, however you want to call it, as a linear function of current. Okay, it's a diode, right? So if you give it some current, it produces some power, and this is more or less linear, right? At least this is what we want to believe for this presentation. So what does this imply? It implies that power at the output of an LED, which is denoted as P of T, P denotes power. Power at the output of the LED is proportional. If it's linear, it is proportional to the current. IT is the current that you feed to an LED. And typically this current IT is some modulation scheme. So SKs are the symbols that we want to transmit, and these are the pulse shapes right? A small pt denotes the pulse shapes, and typically these are orthogonal or orthonormal, however you want to choose it. So IT is this, it's a current that you want to feed to LEDs, and PT is the power at the output of the LEDs. And one thing is, because the diode, it immediately implies that IT has to be positive. Okay, that's what it is. So one constraint in LEDs or VLC system is IT has to be positive for all values of time, otherwise it will be clipped off because it's a diode. That's first implication of using VLC. Let us understand the second implication. LED doesn't act as an oscillator. It's a non-coherent source. When we think about oscillator, we normally think about cos omega naught t, sin omega naught t. Omega naught is an optical frequency. So, but it is not an oscillator, so it cannot produce anything like cos omega naught t or sin omega naught t. It's a non-coherent source. The phases are not known, right? In cos omega naught t and sin omega naught t, the phases are known. These are deterministic signals, right? So you know the phase at all points in time. But because LED is a non-coherent source, it doesn't produce these kind of waveforms. What does this imply? It implies that the electric field that is produced by LED cannot be complex, right? What I mean with this, complex means ET cannot be ER T plus J EIT. So this is a real part, this is an imaginary part. What does this mean? That ET cannot be ERT cos omega naught T minus EIT sin omega naught T. So typically whenever we want to talk about this kind of signal, right, we normally, for mathematical ease and for quick analytical computations, we can represent this kind of signal in form as a complex signal like this, right? So ET, electric field produced by the LED, cannot be like this, right? That is the essence. And if this cannot be like this, that means complex optical modulations are not possible over LED. You cannot have quadrature amplitude modulation over LED. That's not possible. You cannot have OFTM over LED. So we are talking about optical modulations. Okay, such modulation schemes are not possible in over LEDs. Okay, what we can use either pulse position modulation, or we can use on-off key modulation or intensity modulation, right? Because information is in the power or intensity of the light. We also call this as intensity modulation. So simple optical modulation schemes can be used over LEDs, but complex meaning more than one dimension on a single frequency is not possible. Then the third point is this IT can be complex. This can be complex, right? Because what does this mean? That IT is some function like this. Here this omega r is the radio frequency. So that's possible, right? What we have said, the electric field produced by LED cannot be complex, but the current that you are feeding to this LED can be complex. So that means you at subcarrier modulation. So if, for example, if IT is generated using OFTM, that's fine. This is known as subcarrier modulation. That is possible. And once you have an ID like this, you can of course do intensity modulation or on-off keying over LEDs. Okay. So these are the few important points that we have to keep in mind while designing a VLC system. The main essence is subcarrier modulation is possible. In subcarrier modulation, you can generate like a complicated modulation scheme that is possible. What is not possible is complex optical modulation. That's not possible over LEDs. Okay, so let us try to now go a step further. So we have said that we use this IT, which is some function like this, and the current or power or intensity that is produced by LED is proportional to this. Then it goes to a wireless channel, right? What kind of a system is a wireless channel? So typically in signals and system course, we have encountered linear time invariant systems, right? Linear time invariant systems are usually represented by impulse response, but wireless channel is not linear time invariant, right? It's a linear time varying system. What does this mean? That means its impulse response depends upon the time at which you are looking, right? And why is this? Because receiver is basically a mobile receiver. So at different time instances, it will be at different positions. When it is at different positions, it will see a different impulse response. So impulse response that a wireless channel offers is linear time varying. It's not linear time invariant. Okay, and typically that's the case also for VLC. And how to think about the output? Output can, again, for linear time varying systems, it's easy. You just do the convolution of this intensity with this impulse response. If you want to call this given impulse response, we can do its convolution and we can find YT. What happens at the photodiode? Photodiode again produces the current proportional to the signal, the power falling on it. So this YT is power falling on it, right? So it produces a current which is some function. This is known as responsivity. It's usually denoted by flowering R, but I have used a simple R to represent responsivity. So current that is produced by the photodiode is responsivity times the power falling onto the photodiode. Okay. Another and yeah, so now what I have done is, instead of this PD minus lambda, I can also substitute this in here, and it's fine. Okay. So usually what we do, though I have not mentioned this on the slide, is suppose we have this function. If these are orthonormal pulses, that means this can be negative, right? You can only have orthonormality when there's something negative, right? So to cancel out while integrating it. So normally we use some DC bias to make this all positive, but DC bias can be cancelled out at the photodiode. I am not adding the DC bias and so on and so forth. So DC bias is a typical technique which is used to make this IT positive. I have not mentioned this yet. Anyway, let us come back to this. So this is typically the current that is produced in the photodiode. One another way and easier way to think about this is where are my slides? Just give me a second. It's hard to read your own slides because there is something popping onto my right of the screen. Anyway, doesn't worry about this. So YT, immediately, how can I find this? So if PF, this one with cap, is the inverse Fourier transform or the Fourier transform of PT, I can write PT as this, right? Okay, using this Fourier transform relationships. Now, if PT is a signal like this, there is a complex exponential sitting here, and it's an eigenfunction for a linear time invariant system that we know. It's also an eigenfunction for linear time varying system. So the output is the same thing, but this will be multiplied by this system function of this wireless channel. So what is this HFT? It's again the Fourier transform of H lambda t. Okay. So immediately I can find YT is some function like this, and then I can go ahead and I can see that the current that is produced by the photodiode is responsivity times this. It's very simple. I use the same logic. And if I can assume that this is a flat and slow fading channel, what I mean with this, flat means it's normally constant with respect to frequency, and slow fading means it's a very slow function of time. That means I can again treat this as constant with respect to time. So it's both a constant function with respect to frequency and time. Then if I use the mesh filter, then I get a relationship like this. I think it's a simple exercise. Mesh filter is again a linear time invariant system. You just have to do the convolution and so on and so forth. And finally, the current samples that we will have at the output of the mesh filter and the sampler is a signal like this. PT is this En is the energy of this pulse PT. HF is, as I've mentioned, it's for a flat fading channel. If we assume this, and we get some signal like this, R is the responsivity, SK is the sample or symbol that is transmitted at KT instance. So I am looking at the samples at KT. So more or less, this is exactly similar as in any wireless channel. The only difference here that we have to keep in mind is the constraints on IT. Otherwise, it's same. Okay, so now let us compare the radio and intensity modulation and direct detection. Direct detection means we are not using anything complicated at photodiode, a simple photodiode, and the current that is produced by the photodiode is responsivity times the power falling on it. Okay, so that's direct detection. IM stands for intensity modulation. So typically we use intensity modulation or pulse position modulation at optical. For our case, we are concentrating on intensity modulation or on-off key at the transmitter and direct detection at the receiver, because there are not many choices. Okay, let us compare this with radio. Is bandwidth regulated in radio? Yes. Visible light, it is not, right? Is radio signal passing through walls? Yes. For intensity modulation direct detection, no, the signal cannot pass through walls, and it has certain implications. It has less coverage because of this, but it's also highly secure, right? Your signals cannot leak into another room. Multipath fading, I guess you know this. It's there in radio. For intensity modulation direct detection, no. Why? Because wavelength is very small and receiver area is quite large, right? So there is diversity already inbuilt in your receiver. So there is no multipath fading. Okay, it leads to simple link design. Multipath distortion in radio, yes. In intensity modulation direct detection also. Distortion can be, right? Path loss is high in both these systems. Dominant noise in radio is the noise or the signals from other users. In intensity modulation direct detection, it's background light. Input XT in radio signal denotes amplitude, whereas in intensity modulation direct detection, it denotes power, right? That's we have said. Whatever is your current, it gets linearly translated to power. So input is power. Okay, signal to noise ratio is proportional to this mod of xt square dt. So this is signal power basically. And signal to noise ratio is again this. Now what is its implication? Suppose there is 10 dB attenuation offered by a channel, right? 10 dB attenuation, just as an example. So it will decrease the signal to noise ratio by 20 dB in IMDD links. That means if we want to maintain the same signal to noise ratio at the receiver, the power requirement in optical communication or IMDD links is higher. So that's one disadvantage of VLC link. It has a high transmitter power requirement. The average power is proportional to this, average power is proportional to this in IMDD link. So basically, these two things imply that we can choose waveform XT with high peak to average power ratio. Okay, so these are typical differences between radio and IMDD link, and it has also some implications. So now let us look at this VLC link as it is. So we have got data from somewhere, from a base station or from anywhere else, from backbone network, from access network, or from wherever we want to call that. So this is an input data. Typically this is fed to LED, and this LED driver takes some electrical power. It also has some dimming control module. So you want to turn off this LEDs, still you want to have your communication. So for that, we need to have some dimming control. This light falls on photo detector, receive data we get, and then you do some signal processing and you can get some output data. So very simple. So it also has certain challenges. It's not that life is very easy with VLC. It has a lot of challenges, and we are working on the challenges. Still, some challenges are difficult to get rid of. And the first challenge is its field of view misalignment. If the receiver moves too far away from the transmitter, and too far is not too much, it's too far, maybe 20 centimeters. So one, we have a line of sight connection in which the receiver is placed directly under LED, that's line of sight. And now if we laterally move our receiver, let's say by 20 centimeter, we lose our signal. Okay, So there is a field of view misalignment. If you start having a lot of these, what can happen is there can be co-channel interference. Light from this LED can interfere with light from this part of the LEDs. Okay, it's line of sight. If you have some object between your transmitter and receiver, it blocks, right? So there is shadowing effect. It has a small coverage area because this LED doesn't transmit in a much wider cone as in radio signals. There's mobility issue. As you move from one part of the room to another part of the room, you might have to be transmitted or switched to another LED. And so there are some mobility concerns. We need to have dimming support. We need to have flickering support. You need to maintain illumination. And this LEDs also has limited modulation bandwidth. Okay. Now let us look at multipath channel modeling and characterization. So I will not go into the details of this multipath VLC channel model. I will just present the main results, and I will just explain the things which are required to understand those results. So LED and receiver. So LED acts as a transmitter, receiver acts as a photodiode acts as a receiver. Now if I look at this transmitter, it typically transmits light in a cone. That is, imagine this to be a cone. And one important characteristic of this cone is this angle, which is known as LED semi-angle. This is important. Okay, what should be the value of this LED semi-angle for the optimum transmission between LED and receiver? Okay, for example, if we make this too small, like let's say 0 degree or 0.001 degree, what would happen? Intuitively, you can understand that you need to have a lot of sources, because otherwise the light is just falling beneath a source and there's no light anywhere else because the LED semi-angles is too small. So you have a lot of dark spots in the floor. What happens if we make it too large? What will be the problem? The problem will be that this light will begin to hit walls, and this there will be reflection from this wall. So there can be multipath distortion because of this effect. Okay. So LED semi-angle is an important metric, and we have to pay some attention to what should be this LED semi-angle. Another metric is the field of view at the detector. Detector also receives the light in a cone, and this angle of this cone is known as the field of the view. Third important metric is the number of reflections that are taking place at this wall. So for this, there's no reflection. Here there is one reflection, right? So this is non-line of sight path with one reflection. You can have two reflections. So when we are trying to assess this channel model performance, and we have to do this in software, typically you have to define, or you have to choose how many reflections would you consider, because we cannot consider infinite reflections. Okay, so this is third important metric. Okay. And for this result, the simulation parameters that we have chosen is the room dimensions. So 5 meter, 5 meter with 3 meters. So typically a big hall. Transmitter receiver separation is 2.15 meter. LED semi-angle, if it hasn't been explicitly mentioned, is 60 degree. Then there are some other parameters. Responsivity doesn't have much influence. Physical area of photodetector is 1 centimeter square. Field of view 70 degree. Refractive index of concentrator. So we use some optics before the receiver that gives some concentrator gain and so on and so forth. So we will not be talking much about it, but for your if you want to compare these results, so these are the typical simulation parameters with which you can get these results, and that's why I'm talking about them here. And what we want to find is the RMS delay spread. So RMS delay spread simply means typically how wide is your channel impulse response. So channel impulse response is this, and you will be surprised that earlier I had two variables, but now this is sitting with one variable. And this is because this channel impulse response is a function of receiver location. And when the receiver is at a particular location, this is the channel impulse response for that. And this is not dependent on two factors. However, you can have all these channel locations. So receiver might be present anywhere in the room. So you might be having different kind of channel impulse responses based on where the receiver is. And what you can find out this metric, what is the root mean square delay spread. Okay. And that gives us a very good idea of what will be the broadening in my signal. So again, I mentioned, suppose you are feeding an impulse to a linear time invariant system. Impulse to a linear time invariant system, the output is what? The channel impulse response. That means at the output you have a signal of the width corresponding to the channel impulse response. So this width corresponds to the spread in your signal. Okay, how fatty the signal has become. Okay, similarly here we are doing the same thing. We can measure the root mean square delay spread, which gives us a very good idea on how much there is a widening in an input signal. Okay, and based on this RMS delay spread, we can find out the coherence bandwidth, which is of course 1 by tau j and some variable here, and you can have this mean delay spread also. So what we have seen for this simulation, we have these 4 transmitters, and these yellow ones are the transmitter, purple ones are the receiver location. So what you can see is this is the delay spread that we get. It's a function of basically 2 things. So these purple ones are with reflectivity of 0.2. This green one is with a reflectivity of 0.4, blue one 0.6, red one 0.8. So that means as the reflectivity of walls increase, the delay spread increases. Okay. The second point that we have to see is it also depends upon the number of reflections. However, that function is quite weak. That means if we have 1 reflection or 3 reflection, results doesn't change much. All these purple ones are with reflectivity 1, 2, number of reflections 1, 2, and 3. Okay, and the results doesn't change much. And thus we have restrained ourselves to 3 number of reflections. Okay. However, it's a very strong function of the reflectivity. Reflectivity of 0.8 is worst case. So if we have to design a communication system that works, we have to design for the worst case parameter. Now also what we see is this RMS delay spread first decreases with LED semi-angle and then it begins to increase. And why is that? The reason being very simple. When the LED semi-angle is very small, there are a lot of dark spots in the room. And the light falling onto these dark spots is mainly because of reflections. And this light basically has a reduction in delay spread. However, as the LED semi-angle increases, this sorry, I didn't say it correctly. So let us try to think about this again. So let us say that we have an LED semi-angle of 10 degree. Okay, let us look at this point. Now when LED semi-angle decreases below this 10 degree, there are a lot of dark spots and the light falling onto these dark spots is mainly because of reflections. So if we reduce this LED semi-angle below 10 degree, we see an increase in delay spread. Okay, so that's clear. Now let us try to increase the LED semi-angle. Again, the delay spread increases, and this is mainly because as the LED semi-angle increases, of course, the number of reflections increases. Hence, there is an optimum, right, in the LED semi-angle that we can choose, and this number typically varies between 10 to 15 degree. One more point, so we can convert this RMS delay spread also in the coherence bandwidth. So if we look at the worst case number, This is the worst case power. Worst case bandwidth is 30 gigahertz at the right choice of LED semi-angle. That means if you are looking for data rates of, let's say, 1 Gbps or 2 Gbps, 500 Mbps, you do not have to use OFDM. This is the essence. OFDM should only be used when you're looking to go beyond 30 Gbps, which is typically not intended. So we are talking about a small room, hall, 5 meters by 5 meters. Okay. So people have been researching a lot on OFDM for the use in VLC, but they have to keep in mind, is this really required? Because OFDM is not for AWG channel, as you may know. OFDM is when you have a frequency selective channel. And if the coherence bandwidth is so large, 30 gigahertz and so on and so forth, I don't think if we target 1 Gbps data rate, OFDM has to be used. Okay, especially for this small size. So this is the main finding from our work. We can also find the average BER, assuming OK and this direct detection. And again, this average BER we have obtained as an LED, as a function of LED semi-angle at various signal to noise ratio. And we again see that there is an optimum LED semi-angle, again somewhere between 10 to 15 degree. So this is what we have to choose if we have to make the right kind of transmitters. Okay, so this is the average and this is maximum BER, because BER also depends upon where you are in the room, right? So you can have a maximum value of it, you can have a minimum value of it, and you can have an average value. So this is what is plotted. We can have a maximum BER, average BER, and minimum BER according to as a function of signal to noise ratio, and these three BERs are because of your locations in your room, right? For example, if you're directly beneath a source, then we will have minimum BER. If you are towards the edge of the room, we will find us experiencing maximum BER. Okay. So let us look at the one slide. We have a research paper on this. So if you are interested, you can read that. So I'm just presenting the key results. So if my target is to have a maximum BER, worst case, of less than 10 to the power minus 4, if we go to bigger room, 10 meters by 10 meters, 3 meters, and the transmitted power is 10 milliwatt, 10 dBm. Okay. So we can have a data rate of up to 0.9 Gbps. I don't see it, but this is what I think is in the result. I don't see half of my slide. Okay. So that is it, right? So no problem if we are looking or targeting 500 Mbps, absolutely no problem. 100 Mbps, absolutely no problem. A simple on-off keying can work, provided that you have sufficient bandwidth from LEDs. Okay. Yes. So I will skip this. So this is what the understanding that we have obtained from channel modeling. Now let me talk about the modulation schemes that we can use in VLC. So VLC has to support this flicker mitigation and dimming support. Flicker refers to the fluctuation of the brightness of light, and it may result from modulating the light sources for communication. So people may be wondering, if we are working at 500 Mbps, how can we have flicker? You can always have flicker because there is always a possibility of low strings of zeros and ones. When we have low strings of zeros and one, the actual frequency might decrease and you can notice flicker. Okay, and it has very harmful physiological changes in humans, so we have to avoid this at all cost. And avoiding this is easy. You can use run length limited sequences that are typically used to mitigate flicker. You can use some kind of 8-bit to 10-bit coding. These are typically the solutions that you can have. We have also presented some solutions for flicker mitigation that are new and novel. However, I am not including this in the slide because of time constraints. The other thing is dimming. Modulation scheme also has to support dimming, which is you need to maintain communication system while a user arbitrarily dims the light source. So he may be dimming the light source to 1%, 10%, 5%, right? Even when he has done this, you should have a working communication system, right? You should be able to receive your mobile phones even while sleeping. So if we integrate dimming techniques, what we can have? We can have energy efficiency, we can enhance system value, we can facilitate intelligent lighting sources. And there are two approaches to achieve dimming in LED illumination. One is to control the intensity of the light by controlling the current that you are feeding to LEDs. But if we do this, this is known as analog dimming. What happens? The energy efficiency of drivers is reduced, right? And there can be chromatic shift in your LEDs. So that's not good. On the other hand, we can also dim the light sources by using digital dimming, which is by varying the pulse width of your light sources. And when we vary the pulse width, the average may increase or decrease, and as a result of which the dimming may change. So here I will talk about variable on-off keying in more detail, and then VPPM I think can be understood from this variable on-off keying. This was also proposed as a part of the standard. And what is the idea? I think this picture is better to explain this. For example, let's say you want to have 90% of the dimming. Okay, so typically when we use on-off keying, normal on-off keying, 50% of the time we are transmitting a signal and 50% of the time we are not transmitting anything, right? So that is 0.5. Now if you want to have a dimming like 90%, that means we have to transmit a signal 90% of the time. So what we do is we also fill the bit 0 with some dummy signals. So this red color boxes represent the dummy signals. So this is the dummy signal at bit 1 and dummy signal at bit 0, and the data signal is these green boxes. So data is for a very limited period of time, and both bit 1 and bit 0 has a dummy signal. Okay, so of course the average of these two things is higher than 50%, right? So you can make it to 90%. Now if you have to have a dimming less than 50%, what can we do? So normally in OK, the bit 1 has the signal in its entire duration. Now that is not the case here. Even bit 1 has a signal for a smaller period. Okay, so with this two pulses, we can have 10% dimming. So by using this dummy signals whenever it is required, or by having no signals, you can have this variable on-off key. It's very simple. Similarly, we can have variable pulse position modulation, where again, if we want to have a higher dimming, you can have overlapping pulses. If we have less dimming, right, than 50%, you can have what? You can have non-overlapping. Means there are time periods in which there is no pulse, right? Normally in PPM, you have a pulse in a slot and there's no pulse in another slot. Whereas here you have no pulse in many slots. Okay. So the same idea we can use in variable pulse position modulation. Now we have computed the power spectral densities of these various schemes as a function of dimming factor. You see that this changes with dimming factor. That was for variable OK. This is for PPM. Its power spectral density also changes with the dimming factor, and its BR, bit error rate, this is more important, also changes with a dimming factor. So based on different dimming factors that you have, its BR changes, right? So typically we know that gamma or dimming factor of 0.5 is best, and as you increase or reduce the dimming factor in both these cases, the BR increases. Okay, so this is for OK and this is for VPPM. And finally, you can reduce this BR by using a equalizer at the receiver. So what is an equalizer? So already, if we know the channel impulse response, we can always inverse it using an equalizer. We have done that, and these are the results that we have obtained using an equalizer. We can reduce the BR further. So typically we have been implementing these kind of modulation schemes in visible light communication. The last is the multiplexing techniques used in VLC, and the most favorite of my multiplexing technique is non-orthogonal multiple access, What is it? In simple terms, we transmit different power levels to different users. Okay, so we transmit, let's say, a very large power to user 1 and a small power to user 2, depending upon its position. And at receiver, you can use successive interference cancellation for the decoding of these signals. So I will not be going into the details of the successive interference cancellation and NOMA, how it works, but typically you can read about it. I think there's a lot of literature on NOMA that is available. So the main contribution from our research group is proposing a fair power allocation scheme in NOMA. So what we want to do is we want to ensure that each user has an equal BER. So these are the bit error rates for different users. If there are n users, so these are the BER, we want them to be same. And if we want to make sure that this happens, then you need to have a particular power allocation factor. Power allocation factor means how much my power varies compared to the power of my adjacent user. Adjacent means I can sort out the users in the ascending or descending order of their locations. Means if the user is very close or if the user is nearest, I can treat it as the first user. The second nearest user can be treated as the second user, and so on and so forth. Or you can use the other way around. So both these things are possible. So power allocation factor means how much the power of one user varies corresponding to an adjacent user. So this is the power allocation factor that we have derived when we have imposed this constraint, and we have compared with the existing power allocation schemes. There are two of them: gain ratio power allocation and normalized gain with power allocation. So we can see that both in terms of the BR fairness and the throughput fairness, the proposed scheme is much better. So we are more fair to the users. So I'm not putting a lot of emphasis on the hardware work. So that will come later in the slides, later in the presentations. So I'm just trying to give you a general overview of the kind of research activities that we have been doing over the years in the area of visible light communication. I also skipped the MAC protocol and so on and so forth. That would be covered by the next talk. So the demos, so first the Wi-Fi transmitter and receiver, Li-Fi transmitter and receiver was demonstrated at IMC 2019. And so we have demonstrated the video transmission over Li-Fi link. So I think that's already 2 years back. And what we have been able to show is, so this is the transmitter and this is the Li-Fi receiver. And we have been able to transmit the signal between these two laptops. So here the demo goes. So this is the transmitted video and this is the received video. You can see it's working fine. And now we will block this Li-Fi link. Blocking creates shadowing, and as this blocking happens, the received video stops. And when you remove this blocking, the received video continues. Okay, so this is way back for 2 years. The second interesting demo is now we have been trying to integrate this demo using FPGA link. So we have been able to transmit a very high quality video signals over to FPGA boards, and this is the demonstration of that. So you will be told more about these demos after. So yeah, attend those presentations. Okay. The third demonstration that I would like to show you is demonstration on lens design. So lens has to tune itself to the incoming light source so that it couples most of its lights to the photodiode, right? So as the receiver moves, it has to tune itself to the light source, and this is what we are showing here. So I will play out this video again. Yeah, so as the phone moves, its light source changes and the receiver tries to track it and orient itself in the direction of the light so that it can couple maximum light to the photodiode. Okay, So there is the latest Li Fi standard out there, which is ITU G.991, which is for high-speed indoor visible light communication. So you can Google it and read more about this. So here I want to stop my presentation. Thank you so much for your time and attention. If there are any questions, I will be happy to answer them.
Thank you so much for your lightning words, sir.
Are there some questions? First, I cannot.
Yes, sir. Yes, sir. First question is, why are these reflections with such low angles, such as 10 degrees? What is the height of the room?
Height of the room is 3 meters.
It's 3 meters. And like I would like to address the first part also. What are the reflections with this? Why are the reflections with such low angles, such as 10 degrees?
I didn't understand the question clearly. So, so when we are talking about the LED semi-angle, it's an average thing, but light can go out more than 10 degree or even less than 10 degree because it's an Lambertian source, right? 10 degree is light an average number, but of course, it's a Lambertian source, so light can go even outside this 10 degree.
All right.
The
Another,
cone
we
is
have a
realistic representation. It's not transmitting light only as a cone. It can even transmit at a higher angles but with reduced power.
all right. So the next question is, what is the height with a height of 5 meter and 10 degree of FOV? There will be no rays hitting the wall with the current configuration, right?
Sorry, as I have mentioned, so these two questions are related. So as I have mentioned, so when we are saying the Lambertian source and the LED semi-angle, it is LED semi-angle is found where the power is half of the peak power, but there is of course some power outside this 10 degree also. So
All right.
it's not, so when we are representing light being transmitted as a cone, it's not a perfect cone. Light can go out of this cone as well, but with a reduced power. Cone is where the power is half of the peak power.
All right. Another question: how ISI inter-symbol interference happens in visible light communication?
Uh, yeah, so as I have mentioned, if there is a delay spread, so the pulses can overlap, right? So I don't know if I can write or show something, but yeah, so you have to imagine this. So if one pulse, let's say of, let us take some number. Let's say pulse width is 1 millisecond. Okay, the pulses that we are transmitting, and there is intersymbol interference of 2 millisecond. That means this pulse is broadened. So 1 millisecond pulse has now converted itself to a pulse of 3 milliseconds. Now, of course, this pulse will overlap, right? Because early the communication system was designed to be transmitting around 1 kbps if it's 1 millisecond. So of course these pulses will overlap. Whenever the pulses will overlap, you have intersymbol interference.
All right, sir. And another question: can you please reiterate the point you made regarding the OFDM?
The point that I have made about OFDM is OFDM should only be used for frequency selective channels. Frequency selective channels are the channels where the data rate that you want to transmit is more than the coherence bandwidth of the channel. So for example, if my coherence bandwidth is 1 gigahertz, and if the bandwidth of the signal that I'm trying to transmit is 30 gigahertz, that will be a frequency selective channel. Flat fading channel, on the other hand, is the channel where the bandwidth of the signal is much less than the coherence bandwidth. So if my signal bandwidth is 1 gigahertz and if my coherence bandwidth is 30 gigahertz, it's a flat fading channel. Now, when we are using this flat fading channel, there is no use of OFDM, right? Because OFDM will even decrease the spectral efficiency in a flat fading channel, as it has to use the cyclic prefix and other overheads. So there is no advantage of OFTM in a flat fading channel. OFTM should only be used in a frequency selective channel. So when I have presented the results of the coherence bandwidth, and if the coherence bandwidth, I think the result came out to be 30 gigahertz, there is no need to use OFTM if we want to transmit 500 Mbps, because the signal bandwidth is around 500 megahertz and the coherence bandwidth is 30 gigahertz. So that is what I mentioned.
All right, sir. Next question is, how does LED bandwidth affects communication data rate?
So LED bandwidth, so we have three sources here. One is the channel. So in channel, I'm not including transmitter and receiver. Typically in textbook that is included. But let's say channel is this free space thing that we have. And then there is a receiver, and then there is an LED. So we have to ask ourselves a question, which is the most stringent component in terms of the bandwidth out of these three things that we have. Of course, the coherence bandwidth of the channel is 30 gigahertz. That's fine. That doesn't limit our data rate. Photodiodes are also available with high bandwidth, so that is also not a constraint. But LEDs are most constraining component that we have, because its bandwidth is 100 megahertz. That means because of limitations of these LEDs, you have no hope to transmit more than 100 Mbps or 200 Mbps.
All right, sir. How to uplink the request performed from the receiver?
Sorry, how to?
I guess it's talking about, like, we are talking about the downlink, how how we are uploading the data.
Yes. So there will be a presentation in the afternoon in which we are making, we will have a presentation on the uplink for this Li Fi network as well. So this uplink that we have been making is using the radio signal. So it's not visible light, right? So for uplink, we cannot have visible light because otherwise you will have transmitters onto the floor and it will be annoying to various users. So for uplink, we are using the radio signals, and for downlink, we are using visible light. And more about that would come in the presentation in the afternoon.
All right, next question, sir. Sir, how did you solve the problem of interference from the sunlight while transmitting the signal in an open area?
So we have no interference from sunlight because it's basically indoor, right? So that is not a problem. Of course, you have interference from other lighting sources. So that is the problem, and that could be solved quite easily by using two photodiodes. One photodiode senses a signal and that constant illumination source, and another photodiode senses only constant illumination source. And at the receiver, you can use resistors to cancel out one signal from the other, and that is taken care of. So if you have done some optics course, you know the idea of balanced photodiode. It's very similar to that. In balanced photodiode, you use two photodiodes to cancel out relative intensity noise. Similarly, we can use two photodiodes to cancel out the constant illumination source that's not having data.
All right, and it goes for the same for the ambient light sources, right?
Yeah.
All right.
Of course, we have not had any issues with sunlight, but you can use the same technique to cancel out the sunlight.
All right. Then next question is, how much max bandwidth throughput we can achieve?
I don't know. So it depends upon how good your LED drivers can be, and what are you also looking for other solutions in VLC. So for example, if you're using lasers in VLC, if you have those sources, then of course you can have maybe 10 Gbps or 40 Gbps. If you're looking at infrared sources, again 40 Gbps is possible. I think few days before I heard the presentation from IIT Bangalore where they are using infrared sources and they have been able to push up to 40 Gbps. So that's possible over visible light, and if we are focusing only on LEDs, I think going beyond, definitely beyond 500 Mbps is definitely not possible. So until and unless we make significant improvement in the sources that we have.
All right, sir. Next question is, in case of when ISI is happening, when do we use cyclic prefix and when should we use equalizers?
It's a good question. So you can use both. You can use equalizers as well as the cyclic prefix. So normally whenever we use OFDM, we need to use cyclic prefix. That makes the demodulation of OFDM quite easy. And if we are focusing on single frequencies, then we can use equalizers. And you can also combine the two. So there are several research papers which are also combining equalizers and cyclic prefix. So you can have the best of the both worlds. But my general understanding on the subject is, if you do not use OFDM, if you are just transmitting single frequency, then I think we should use equalizers. If you use OFDM, then we use cyclic prefix. You can of course combine this cyclic prefix and equalizers, so you can have OFDM links where also we are using both equalizers and cyclic prefix. That will give you some advantage, but the advantage wouldn't be significant. Yeah.
Right. Next question is about light sources. So we are using a coherent or non-coherent light source, and what's the difference between if we use one of them?
So coherent source, as I have mentioned, is it's basically LED is a non-coherent source and laser is a coherent source. So coherent source means that you know the phase of the electric field at all points in time. So laser is an extremely high coherent source, so it can produce electric fields like cos omega t and sin omega t. So you can do complex optical modulations over lasers. But over LEDs, this non-coherent source, that means the space of the electric field is not known at all points in time. So you cannot use LEDs to produce cos omega naught t or sin omega naught t. That's not possible, right? Because it's a non-coherent source. Once you do not have those kind of waveforms produced by an LED, you cannot use complex modulation schemes, complex optical modulation schemes over LEDs. So LEDs are cheaper. LEDs are have a good illumination also, but they come with a disadvantage that they are.
All right, so next question, it asks, are there any industrial applications for this visible light communication?
There are a lot of industrial applications for visible light communication. I think there is Alumni has used Li Fi to in airplanes, so they have commercial solution for that. So over the passenger seat they have a transmitter, so you can serve or stream the videos from that transmitter to your laptop in airplane. So but the sources and receivers are quite stationary there. Then I think in February 2021 there is one company, Hardik, Sony. They have used Li Fi in hospitals for corona patients, because they have claimed it as a more healthier solution. So they have used this in 2 streets in Gujarat. So they are also looking for this. And then there is a Wipro, who is also working very aggressively on Li Fi solutions. There is Pure Li Fi from Harold Haas, who has been working on Li Fi solutions. There is Huawei. A lot of industries are looking at Li Fi, and I think in at least in some years from now, Li Fi will be a solution which will coexist with Wi-Fi. If it doesn't replace Wi-Fi, it will definitely coexist with Wi-Fi, and it can provide a very high-speed links from transmitter to receiver. And one most important application of Li Fi, and in which I believe is it's a very healthy option. It's a health-safe option. It has no hazards. So nowadays, awareness of human beings towards the hazardous impacts of radio waves is increasing. So you have seen that in rollout of 5G, there has been a lot of protest because it says that we have been increasing exposure to radio waves. So I think Li-Fi can come in there. It can be a potential alternative to at least indoor solutions. And we live in our office and home all the time, so we will like to be less exposed to high radio frequencies. Rather, we will like to be exposed to the light, which is a safer option.
All right, sir. Next question is why co-channel interference despite having terahertz bandwidth?
No, so there is a misconception here. So terahertz is not the bandwidth that is available on Li-Fi. So as I've said, bandwidth is constrained by the most stringent component in the link. The most stringent component in the link is transmitter. It's 100 megahertz, right? So we do not have terahertz bandwidth. We have only bandwidth up to 100 megahertz available in the visible light communication based Li-Fi solutions. Okay, so that's a misconception that we have terahertz bandwidth. So that is not. And secondly, the interference has nothing to do with the bandwidth. It has to do with the fact that if two LEDs are using the same wavelength and they are transmitting at the same time, and if the signal reaches to a single user at the same time, then there will be interference. What is interference? It is the superimposition of two signals which you cannot separate. So if one is transmitting one and the other one is transmitting zero, you have resultant signals one at your user, and user has no way to deduct or to conclude who has transmitted what. That's what an interference is. It happens whenever two light sources are using the same wavelength and they are transmitting a simple modulation schemes like OK. There will be interference irrespective of whatever bandwidth you may have.
All right, sir. Next question is LED has bandwidth in megahertz, but we transmit data in Gbps, right? So does it cause any problems like mismatch or something?
No. I haven't said that. I have said for visible light communication, if we are using phosphor coated LEDs and blue filters, then we can have bandwidth of LEDs up to 100 megahertz, and at best what you can transmit is 200 Mbps at best. You cannot go up to 1 Gbps, but if you are using other transmitter solutions, if you are using that in gigahertz, then you can go up to 1 Gbps. Over LEDs, simple phosphor coated LEDs, I think getting to 1 Gbps is a miracle. I don't believe in any numbers like that.
All right, sir. Next question is a very interesting one. Can we use this whole VNC communication underwater, and does sunlight affect it?
Yes, one of not the primary, but one of the important applications of VLC link is in underwater communication. So people have been using it, and yeah, and in underwater the problem is very high attenuation offered by the channel. So that is the problem that people have been trying to solve using error control codes. Yeah, other than that, it can be used for underwater communication. I don't see a problem.
All right, sir. As we are reaching a time limit, so there are more questions. I'll request you to answer them directly in the chat. The questions we are not able to cover in this session will be answered during the session or at the end of the session. All right?
Okay. Thank you, Utkarsh. Thank you everyone for attending my seminar. And I will also like to take this opportunity to extend the collaboration of IIT Delhi between other institutes as well. So if you want to collaborate with us in this work, you may please write us an email or talk on my landline phone. And if there is any opportunity in any way, if I can assist you or collaborate with you, that will be great. Thank you so much.
Thank you so much for your kind words, sir. All right. I'd like to invite Mr. A.K. Mittal, who is associated with TSD SI as advisor with special focus on standardization in wireless and wireline system. He has represented Government of India in various bilateral and multilateral international meetings, and he's here to give an overview of TSDSI. I request you please turn on your mic and webcam, sir, and please take over the session.
Yeah, will I have the presentation right here? Or you are displaying?
I've sent you a prompt. Please select your presentation.
Okay. Is my screen visible?
Yes, sir.
Okay, thank you, everyone. I'm able to see my cam myself, not the screen. Should I cut it?
Just click on the slideshow, sir. You can just go
Yeah,
to the slideshow.
but I'm seeing my. Or I will just remove it. Is it okay now? Right.
Yes, sir.
So, just a minute. Why am I not able to show it? So today we are going to talk about briefly about TSDSI, its constitution, how it works, what are its achievements. So we this is an introduction about TSDSI. It's a non-profit organization registered as a society, and
I'm sorry, sir.
Yeah.
If you may make it in full screen mode, the slide.
It's okay. It's not full screen mode. Sorry, just a minute. I was seeing the full screen.
Yeah, thank you, sir.
It's okay now. Oh, thank you.
Yes, thank you.
So we are a non-profit society, membership driven, and we have members from. We will show you in the other slides that from what type of industry segments we have the members. And the basic purpose is that we make standards for Indian requirements and also reflect Indian requirements into international standards. And by doing so, there is also an opportunity to incorporate Indian IPs into global telecom standards. And we work with openness, transparency, consensus-driven organization, and provide a uniform level playing field. So our membership, as you can see, is from telecom operators, industry associations, manufacturers, R&D labs, public sector undertakings, academia, and all. So these are the broad industry categories from where our members come. And members are divided into three categories mainly: corporate members, associate members, and guest or observers. So corporates are those who are normal, industry bodies, or sorry, industry organizations that I shown in the upper part of the slide. And associate members are actually either the foreign entities or industry associations. For example, we have COI or ICEA, and there are other bodies who are industry associations. They can become associate members. And difference is that corporate members have all the voting rights in and rights to hold various positions in TSDSI. Associate members do not have voting rights. Guests are invited for specific purposes, and observers are those organizations who have intention to become member of TSDSI but want to see it's working for some time, so they are given 6 months time as observer. This is the structure of TSDSI. We have a general body consisting of all the members. It elects a governing council, and the chair of governing council and general body is same. And currently we have chair as Mr. NG Subramaniam. He is from TCS. Vice chair is Satish Chamdagni from Jio, and treasurer is Agarwal, DK Agarwal from BSNL. And governing council has 29 members, 21 elected members, and 8 nominees from the government, different mostly from DOT and MIT. And this functions, the technical work is actually done in two study groups. One is called study group networks, and another is called study group services and solutions. And you can see on the slide, the work of study group networks is entirely on the network side, and services and solutions works on the applications and security and related aspects. And on the bottom part, you see the structure of secretariat, and secretariat is headed by Director General Pamela Kumar. And governing council is assisted by a number of standing committees. Some names are here: Standardization Committee, Roadmap Committee, Transposition, Finance, Rules and Regulation, IP, and so many others. And we are well plugged into international standardization system or ecosystem, and the major ones are 3GPP. As you know, 3GPP is the global organization or a consortium of standards bodies, where we are one of the standard body member organizational partner, and it works on the global mobile standards, whatever you know as 3G, 4G, and 5G. It is all coming from 3GPP. Of course, TSDSI has 5GI to its credit. 1M2M is working on, this is a machine-to-machine communication consortium, and it works on service layer standards for machine-to-machine communication, and its best known use is for the smart cities, various verticals in the smart cities, and other applications where machine-to-machine communication is required. Global standard coordination is also a collaboration of standards bodies. We are a member of this, and in ITU we are selectively members of two study groups. In ITU radio communication, we are study group 5 member, which works on the mobile communication part, terrestrial mobile communication, and ITU-T study group 15, which works on the optical communications. And these is the details of various alliances, MOUs we have, where we collaborate for various activities of TSDSI. Now, this is briefly, before we go into how do we make standards, we should know what it aims to achieve. I think most of you will know why standards are needed. So it's briefly mentioned that standards can resolve the existing problem, or can upgrade the technology, or you want to standardize the existing technology or practice. Something is running by default, so if something can be made a de facto standard, or some new technologies to be brought in. As you see in mobile market, from 2G to 3G to 4G and now 5G, technology has changed. So this has been made possible by standards. Now market requires certain things to be done, so that becomes a trigger for bringing in new standards. Interoperability is the requirement, is also the advantage. So once you have equipment of same standard, then it can interoperate. There is the reliability. Then it also addresses regulatory compliance. And once you have standards-based manufacturing, then economies of scale are achieved, and then competition is fair. And who are involved? And all these who are involved are the other categories from which we have members in TSDSI also: product manufacturers, chip manufacturers, test equipment, R&D, telecom service providers, academia, and government. These are the broad categories of organizations who are involved in standards. And this is a block schematic that how standard is actually made. So some idea has to emerge. So we saw a list in the previous slides that where an idea can be generated, whether market requirement or technology requirement, etc., etc. So the idea has to emerge. It has to be defined, because in standards it is very important to define what we want to actually achieve. So scope has to be defined. It has to be converted to a proposal in the standard body. And because you want it to be acceptable to a wider ecosystem, so you need support of members. That okay, somebody brings in a proposal, so members should support that. Okay, we are ready to work. So there is the acceptance of the proposal. You develop the standard, draft it. Drafting is one of the most important parts to convey the right meaning, that whatever is the scope we had in second block, the top, that is reflected by drafting, and issue the standard. And adoption and implementation is the most important part. You have to issue a standard, but then it has to be adopted and by the market and implemented. In TSDSI, how do we do it? And this is the very generic, this also can be called a generic way of standards development. There is a pre-standards time, there is a standardization time, and there is a post-standardization segment. Now in the pre-standards, what we saw in one of the slides earlier, the idea has to be generated and it can be sourced from government requirements, collaboration with the industry and other SDOs, research and innovation. Then you can create a technology roadmap for the standard body. And then you have various reports, white papers, research papers, and so many other collaborations. So all that, those things create an idea, which is converted into a proposal, which is called new item proposal or a NIP. So this is the starting point of standard formulation. And then it goes to a study group. For example, if in top of TSDSI, there are 2 study groups, study group networks and services, network and other is services. So depending on which in the scope of the NIP, it can go to either of the study groups. And then it can lead to either a work item or a study item. Work item means when the proposal leads to a standard directly, or a study item where the proposal requires a study first before the normative work or standard for it is taken up. So work item leads to a standard and a study item leads to a report. So study item can end at a report if no further action is thought that some standard can be made. Otherwise, the loop restarts, it come back to NIP, and then again it converts into work item and a draft standard. One of the important steps in formulation of a standard is intellectual property rights. So members may have their IPs, and the IPR policy of TSDSI and similar other SDOs, they have a requirement on the members that they will declare their IPs in the standard which is being developed in the SDO. So our TSDSI members are bound by the IPR policy, but they have a freedom of the timing when they want to declare. There are formats in which they have to declare and all that. So once all this activity is complete, it becomes a TSDSI standard. But before that, it has to go through the general body. General body has to examine it and pass it. Then only it becomes a standard which can be published. Another method of standards is by transposition, that we have membership with 3GPP and 1M2M as a organizational partner or a partner type 1 respectively. So we are, have a right to transpose their specifications by giving our number, and it becomes a TSDSI specification. So that process of converting specifications of 3GP, 1M2M or similar other organizations, if we have some arrangement with them, is called a transposition. And after transposition also, again, IP declaration is required because our members have contributed to 3GPP and 1M2M, and if they have IP, they declare here, and again it follows the process of making a standard through general body, right? And then after a TSI standard is made, our rules provide that we send it to Telecom Engineering Center, which is a part of DOT, for adoption as a national standard. And international standard is written here because whatever 3GPP and 1M2M we transpose, they are, because they are international consortiums, so they also become international standard. And post standard is an activity, as we saw in one of the block diagrams, the earlier slide, is the activity where the market should adopt and implement the standard. So these are some breakups of what are the possible actions and the areas which can be covered under post standard activity. So some of the activities of the pre-standards area, what have been done by TSDSI are in the type of workshops which we done, for example, AI/ML, public protection, disaster relief, 5G radio interface technology, drone communications, and we also create TSDSI roadmap where we call members and non-members to generate ideas for a 2 to 3 years time frame. And we publish it on our website. Currently, roadmap 1.0 is published, and roadmap 2.0 is under formulation. It will be ready by end of this year. And we also create task forces and special interest group, which are now called technology item proposal forums, where non-members can also participate, and we can generate ideas which can go into the roadmap, or sometimes directly into the study groups as a new item proposal. So roadmap example is given, the roadmap version 1 which was created, we got about 50 ideas. They were filtered from the point of view of their suitability and current scope of technology. And most important part of it is that members should support the idea which has been generated, because the work in the study group will be done by the members. So these are some of the ideas which were finally shortlisted, and most of them actually landed into study groups for formulation of a report or a standard. Now, these are the ideas which have come in roadmap version 2.0 exercise, and interestingly, many of them, while we are deliberating what should go into the roadmap and working with the members, many of these items have gone into the study groups and work on technical report or standard is on. So top green part shows whatever has gone to study group, and actually many more have gone, and others are under discussion to be reflected in the roadmap. So this is an example of some important items which are being worked upon in study groups. So study group network, chair is Satish Jamadharmi, and vice chair is Mr. Prakash, he is from CDOT. And the important parts, for example, are 6 GHz spectrum usage for IMT applications and license exempt applications, because this study is required because this band is shared with satellite communications. And dynamic spectrum access, we have started work on 6G use case requirements and technologies. So here we have taken a lead, and we have actually sent our proposals to ITU also. So the VLC and Li Fi, as you see in the last bullet, there is a study item on VLC Li Fi in the study group currently, which is being led by IIT Delhi, but many members are supporting it. Study group services and solutions. So they have, you see the areas ranging from cloud interoperability and security and drones, right up to smart applications, quantum cryptography and all. There is a wide range of topics on which most of these items are in the study phase right now. And later, once the reports are published, it will be decided which area we go on making a standard. This is summary of technical reports and standards published. So study group networks and study group services and solutions. The published standards in the last column, they also include, most of them are actually the transpose standards from 3GPP and 1M2M. Reports are our TSDSI reports basically. So we also do outreach activities to non-member organizations so that they understand about TSDSI and the scope of standardization. So we have a vision. I will not go into detail of this, and just to have an outreach, and we had released white paper on a startup ecosystem. In fact, a lot of startups are our members now. Standards-driven research we are promoting. Then global forums, we have partnership, and we organize events on various technology aspects and invite non-members also to those events. We have TSA expert talk series, and we have our a showpiece event, which is TSDSI technical deep dive, which we do it every year in October. And this time, this was the current 3rd year running that we will have or this is the 4th year running, we will have our event, details of which are available on our website. So some of the accomplishments which we have, we can showcase are, the first bullet is the most important one. TSDSI has submitted a radio interface technology to ITUR, which is an upgradation of 3GPP 5G technology, and it is now part of the international standard ITUR recommendation M.2.2150. It has enhancements over coverage, spectrum efficiency, and latency. And then TSI standard on IMT advanced. This is a transpose standard of 3GPP LTE, and also M2M release 2. They have become national standards. TSDSI also developed CPRI front haul transport standard, which is a standard for the link between the distribution unit and the transmitter at the tower top. Is on CPRI standard, but it is CPRI front haul transport, mapping on the OTN. So this is a standard which has gone to TEC for adoption. There is a stable dialogue going on with them. Navic is another one achievement that, like you see GPS in your phones, Navic is a ISRO-based, ISRO-developed system, which was not part of 3GPP mobile specifications. So with the initiative of TSSI members, it has been now adopted as 3GPP standard in release 16. Cloud interoperability report has been released and work on standard is being done. These are some names of the reports. These come from the topics which we already saw in the work areas of study group networks and study groups solution solutions. Now this is the work related to Vlc Li Fi. I have picked up from the proposal objectives which have been indicated in the document which is working on, which the work is on in the study group networks. So this will cover actually the current standards it will study and identify gaps and suggest possible areas where further standardization activity can be taken up. And the main objective, ultimate objective of this study is to identify opportunities for proposing ultra high speed PHY layer, 10 Gbps throughput, and MAC layer for multi-user access and handover techniques for hybrid Li Fi and RF network. So this is a bit futuristic, but the aim of the report is also to cover these aspects. And it will definitely then look into the several application areas like telecom infrastructure, defense, building infrastructure. These are the application areas, and how Li Fi can be used as also will be part of the study. So after seeing all this, one conclusion which we can draw, or the objective of TSDSI which can conclude, is that there are government, there is industry, academia, startups, they are our members, and all have to work towards the same goal, and sometimes they don't work towards the same goal. So TSDSI actually provides a platform for all of them to come together and work towards a common objective. Because every work in TSDSI is done in collaboration and with support and with consensus and with level playing field. So every member can get involved in creating reports and standards with a common objective. So this is a platform, and all these sectors which are shown here, they are all there in TSDSI, and work is going on. It has really picked up in the last 2-3 years. A lot of work has been picked up, and you see 5GI standard also got developed in the last 2 years and so. And how TSDSI has grown, started in January 2014 with 11 members, and now we have 79. Actually, it has grown to 82 as we talk. And these are some of the works which were handled. There is a list I will not go into again because we have already seen in the previous slides. Thank you very much. That's all I had. Are there any questions, please?
Thank you for your kind words, sir. Chat, do you have any questions? Sir, I have a question. Like, I personally want to ask you.
Yes, please.
Does TSI provide any program for undergraduate students to take part in such activities?
Sorry, can you repeat? Your voice was a bit low.
All right. Like TSDSI, does it have some programs for undergraduate students to take part in such standardization and all activity, some experimentation work or study?
Actually, not exactly, because it is a membership driven organization, and the standard work is done by the members. And we do invite guests, but they are also experts in their areas. Of course, the students can participate in our various pre-standards activities like workshops and other events, and we can invite them, and they can even, their participation role can be decided how they can contribute to such events.
All right, sir. Thank you so much for your enlightening words, sir.
Thank you. Thank you very much.
Utkarsh, this is Bindu Srivastav. I just wanted to add to what Mr. Mittal has just mentioned. May I? I'll just take 30 seconds.
Sure, ma'am. Yes, ma'am.
Thank you. Thank you. So, although TSTSI, works on deep technical activities and academia, most academic institutions are our members, and faculty and researchers, especially PhDs and some postgrads, are working with us in various study items. There are possibility. It is possible for the undergrad students to work with volunteer for some activities with TSTSI. Maybe like like some of you students are helping organize this workshop. So we can explore how undergrad students can associate with TSTSI through your faculty. So I hope you
All
keep
right,
that in
ma'am.
mind.
Yes.
Thank you.
Thank you so much for that information, ma'am. Our next speaker is PhD scholar at IIT Delhi, and her area of research includes visible light communication and passive optical network. She has done her master's in optoelectronics and optical communication from IIT Delhi, and she's now here to talk about MAC protocols and solutions. Over to you, ma'am. I'd like to request Ms. Anjali to please turn on your camera and take up this session.
Hello, good morning to all of you. Utkarsh, kindly can you play the video?
Yes.
A video from my lecture.
A very good morning to all of you. I'm very thankful to IITD and TSTSI for providing me the opportunity of sharing my knowledge with all of you. My name is Anjali Gupta and I'm a research scholar at IIT Delhi. My topic of research is Media Access Protocols in Li Fi. And the topic of my talk today is Media Access Control Protocols and Solutions for Visible Light Communication. In this talk, we initially need to know what a MAC layer is. So for that, we will be looking at the OSI model. The idea is that we want to send some data from host 1 to host 2 over the internet. So what are the processes that are required at host 1 and the intermediate nodes in the internet and at the host 2? So the OSI model presents the prototype of all those processes. OSI model says that we require 7 parallel processes at the host 1, and at the intermediate layers we require at most 3 to 4 processes, and at host 2 all the processes that are running at host 1 must be running at host 2. But today we use TCP IP model, so all the processes stays the same, but the work of 3 or more processes is done by a single process, and we are now stuck with 4 layers. Application layer basically provides the interface to the user. Transport layer provides the checkpoints so that the data is not lost over the link. So internet layer provides the routing information. So over the internet there are many nodes. What is the hopping pattern that we must follow to reach at host 2? And last but not the least is the network interface layer that we are interested in. So in the OSI model, the network interface layer was divided into 2 parts, data link and physical layer. The physical layer was just discussed by Professor Abhishek Dixit. We are not more interested in data link layer, where all the media access control processes are happening. We will come to it why it is called interface layer. But before that, let us take up an example. Let us say host 1 wanted to send some data to host 2. Here we wanted to download some movie. So the instruction is I want to download a movie. So this instruction in host 1 goes to the transport layer. Transport layer adds some header so that it can be reliably reached to host 2. And the internet layer adds the destination address, that is the address of host 2. And the network interface layer adds 2 headers. One is physical layer header and another is MAC header. Our computer is connected to internet through some interface. Here's a wire interface is shown, let us say the Ethernet cable. So the node must have an Ethernet cable interface, the Ethernet jack. It receives the packet and optionally it can change the interface, like Let us say it wanted to send the data on an optical fiber. So it inserts the headers, put different headers here, and node must have now the optic fiber interface, and similarly the process follows until the packet reaches the host. Here the reverse process happens and the headers are removed at every process, and finally we receive the information. So why do we need to know this? The focus is network interface layer. All the upper layers in a host stays the same. Whenever we change an interface or technology, we just change these two layers. We usually change these two layers. In our case for Li Fi, we need to implement these two layers, and all the other layers are already present in the systems. We are presenting some examples where we are providing these two layers for different technologies. We all know that our laptops doesn't have SIM card slot. In case we are sitting in a train, there is no Wi-Fi, there is no Ethernet. How do we connect to the internet? We can use 4G dongle. So here what is happening? The 4G dongle has the interface layer and all other layers at the laptop stays the same. Similarly, we wanted to connect to Gigabit Ethernet network. But let us say our laptop doesn't have Ethernet port, so what we do? We use an Gigabit Ethernet network adapter. So this adapter contains the interface layer and we are now connected to the internet. Here one thing that we must take care is physical layer is present in the adapter. So we can either implement MAC layer in the adapter or MAC layer can be implemented in the system using some drivers. So whenever we connect this adapter, drivers get automatically downloaded. So there can be some functionality of the Mac that is implemented. Now we know that we need to implement Phi layer and Mac layer to develop a Li Fi device which might look like a network interface card that can be directly integrated to the motherboard or a dongle-like device. However, we have yet not discussed the importance of medium access control. As the name itself suggests, it provides control over the medium, that is a channel, and how to access it. This is particularly pronounced when multiple users use same channel for sending their data. Let us consider the case of Li Fi only. Here we have access point that works like Wi-Fi router. We also call it coordinator. It can send data from the light to user 1 and 2 in the downstream. The access point directly broadcasts the data, so user 1 and 2 receive the same data and they filter out whatever data is addressed to them. However, when user 1 or 2 wants to send the data to the access point, it can be possible that user 1 and 2 start sending data at the same time. So in that case, collision occurs. So what is collision? Let us say user 1 sends a waveform to the access point that looks like this. So it contains some data. And user 2 simultaneously sends a waveform that looks like this. Access point was expecting a signal that was between some range. We call it 0 to 3 volt range in the example. But the access point now receives data which has very high voltage and knows that there is some problem that happened in the upstream. So to avoid such problem of collision, medium access control layer provide the medium access control algorithms so that user 1 and 2 doesn't send data at the same time. Medium access control layer also provide functionalities that are specific to the physical layer. So there are different modulation schemes that we are using, how to assign different users the different channels and different powers, different time slots. All these things are handled by medium access control. Medium access controller also deal with the packet loss that happens at the physical layer by using retransmissions and error control functions. Medium access can also provide authentication and security. So medium access control layer, it gets the data from the upper layers, that is the networking layer, and adds some header over it to provide all these functionalities that are specific to Phi. and send it on the Wi-Fi layer. So let us say we deployed Wi-Fi in an office setting, and this is the setting, but the users are not getting enough bandwidth, so we want to add some other access point. However, we cannot add another access point in such a scenario because it is already saturated. If we add some other access point, we will get a lot of interference and will face problems. So in such a case, what we can do is we can use infrastructure LEDs and make them work as Li-Fi access points. So in that case, we have many of the access points of the Li-Fi, and we can get very high bandwidth per user. So far, everything looks good, and we must be using Li-Fi. However, there are several challenges of a Li-Fi network. First one is field of view misalignment. Light is highly directional. So the device that we want to use to connect to the access point, it can have very different orientation as shown in this case. Let us say this user wanted to send the data to LED or access point. However, the received signal strengths are very low because of field of view misalignment. Second challenge is co-channel interference. All the access points are using same wavelengths. So in this case, when LED1 or access point 1 sends the data in downstream and LED2 sends the data in downstream, the data is collided or the user cannot guess what data was sent by what access point. So this need to be mitigated. Another problem is blockage or line of sight. Since light is highly directional, so the light can be blocked by the infrastructure inside the room or mobile users. So the signal strength might be very low or there is no communication path and user cannot connect to the internet at all. So how to deal with such a problem? Moreover, we are using same medium for access. We do need multiple access control in such a scenario. Fourth problem is coverage area. Li-Fi access points provide very small coverage area. Therefore, if a user is moving inside the network, it requires very frequent handovers. Handovers is fine, but having frequent handover is again a problem. Li-Fi also have problem of flickering, illumination and dimming support. So when we are using the LED access points, we need to take care that the room has sufficient illumination and the power is within the limits so that it doesn't interfere with normal human working. It also must be able to support light dimming. Moreover, LED access points must not cause flickering. We have already introduced media access controller and its importance. Now I'll be discussing about media access controller of Wi-Fi and Zigbee. Why do we need to discuss that is because the current standards of Li-Fi and VLC MAC are developed on the basis of these standards. So the idea of Wi-Fi was to provide wireless local area networks and its first standards was introduced in 1997. IEEE 802.11 provided internet access to wireless users. However, in 2003, IEEE 802.15.4 was developed to provide low data rate and non-complex devices to form a personal area network. So initially the standard was developed, it didn't provide access to the internet. Therefore, various commercial standard bodies came together to develop upper layers for IEEE 802.15.4. Some examples are Zigbee Wireless HART, MyWi, etc. So the application of IEEE 802.11 Wi-Fi is providing internet access to highly mobile devices, and IEEE 802.15.4 it provided the connectivity between sensor nodes, semi-mobile devices. But nowadays, because of the era of Internet of Things in smart cities, the upper layers of IEEE 802.15.4 are developed to provide internet access using IPv6 protocol. For example, 6LoWPAN, Zigbee 3, etc. So IEEE 802.11 didn't focus much on the battery. However, the focus of IEEE 802.15.4 was to save energy such that the devices can last for several months or years. The network type that Wi-Fi supported was local area network. However, IEEE 802.15.4 supported personal area networks. The file layer of Wi-Fi is quite complex, and complex modulation schemes are used to provide high data rate and high throughput. A few examples of complex modulation techniques are orthogonal frequency division multiple access, 1024 quadrature amplitude modulation, multiple input, multiple output manner. However, IEEE 802.15.4 use simple modulation techniques like pulse position modulation and on-off key. Now, based on Wi-Fi and Zigbee, where do Li Fi and VLC stand? Li Fi standards are currently not ready. Li Fi is standardized along with Wi-Fi in 802.11 BB standard. In this standard, the major focus is minimal changes to the Wi-Fi so that Li Fi can be implemented in the same module as that of Wi-Fi. However, VLC, visible light communication, now optical wireless communication, was first standardized in 802.15.7 in 2011 and later revised in 2019. 802.15.7 is derived from IEEE 802.15.4 and hence it takes care of low battery of the devices. There are very few competitors to deploy Li Fi or VLC networks, and whatever solution they are providing are their proprietary solutions. In Li Fi, the major concern is that the mobile users in the indoor environments must be covered, so the highly mobile users must be handled by a Li Fi or Wi-Fi heterogeneous network. However, VLC focuses on standalone VLC network. The file layer of Wi-Fi is expected to be complex. It might have several complex modulation techniques like orthogonal frequency division multiplexing, multiple input, multiple output, MIMO, or non-orthogonal multiple access. However, VLC still uses very simple modulation schemes like on-off keying and variable pulse position modulation. In Li Fi standard or 802.11 BB standard, the horizontal and vertical handovers will be considered. However, in VLC, a cell-based research mechanism is used to handle the mobility. Now, as we have already defined that Li Fi and VLC is derived from Wi-Fi and Zigbee media access controllers. Therefore, media access control algorithms are similar to Wi-Fi and Zigbee. In the VLC standard or 802.15.7, simple CSMA CA is suggested. Let us see how this works. There is a VLC or LED access point, and these are the VLC users. So in a simple CSMA CA, whenever a user or access point wants to send the data, it must go in back off, and whenever the channel is free, the data can be sent. Let us say channel is detected idle by this user. So there is no energy in the channel and source is ready to send the data. It sends the data, AP receives it. However, we must see that due to directionality, it may be possible that other users do not get the information that the channel is busy and they can also send the data in the same time. Therefore, collision can happen. Now after sending the data, source receives the reply from the access point and it can get the acknowledgement which is received by all the users. Now the collision can happen in this part of the communication. So how to deal with the problem? In practical scenarios, it is suggested by the researchers to use two different wavelengths in upstream and downstream. That is, in downstream from LED end, the visible light can be used that serve the purpose of both illumination and communication, but in upstream use IR, that is infrared light, so that the user does not face the problem of continuous blinking of the light. So therefore, two different wavelengths are used in this case. A busy tone signal is suggested to deal with the problem of collision in CSMA-CA in Li Fi networks. Let us say source is again sensing the channel free and starts sending the data. So channel is detected idle and it sends the data, and at the same time AP access point sends a signal in the downstream which is a busy tone signal, so that other users does not send the data at the same time, and hence collision can be avoided. So we can see that access point is receiving data and at the same time it is sending the busy tone. So the busy tone is extended till the time it receives the acknowledgement, and busy tone is received by everyone on the network, and after that time acknowledgement is sent. So when the acknowledgement is sent, other users get the signal that channel is still busy, so they do not send the data. Now we can still get the collision if two or more users sense the channel at the same time. However, the collision probability has vastly reduced by using busy tone signal. There is another improvement that has been suggested over CSMA-CA with busy tone. It was suggested that, let us say, source sends the channel idle. So along with busy tone signal, what if we send the data? So if data is coming in downstream, all the users must know that the channel is still busy, so they do not send the data. In this case, the spectral efficiency of the system has been improved, and similarly, acknowledgement can be sent at the same time. There is another algorithm that is suggested for implementing media access control. In this algorithm, a centralized controller-based resource allocation scheme is proposed. This is a time division duplexing scheme. The time is divided in cycles. Each cycle consists of access procedure and data transmit procedure. During the access procedure, all the users contained the channel using CSMA-CA in the access procedure to transmit their bandwidth requirement to the access point, and at the end of the access procedure, the access point sends the information that when each user can send the data in upstream. In this way, the slots are assigned to every user in the grant message so that they can send the data collision free. Moreover, access point can directly broadcast the data in downstream. In this way, we can achieve very high spectral efficiency and throughput. For the sake of completeness, we have also included a slide on MAC algorithms using channelization techniques. Channelization techniques depend upon the modulation schemes of the file layer. So there are different modulation schemes that can be used for channelization techniques, like optical orthogonal frequency division multiplexing can be used for multiple access in upstream. Similarly, optical code division multiple access can also be used to handle data of multiple users in upstream. Color shift keying and non-orthogonal multiple access is also discussed in the literature, which can also be used in the upstream for handling multiple users. However, there is no hardware implementation available, and it is still a question whether we can implement these channelization techniques or not in the Li Fi networks. Next, we will be discussing about the handovers in Li Fi network. The handover decision is usually taken on the basis of the received signal strength. So if the user is receiving less energy from the access point, or the access point is receiving less energy from the connected user, so the handover decision can take place, whether the user must be connected to the neighboring access point or not, or whether user must initiate whether it wants to connect to the access point or not. These handover procedures are also based on user trajectory prediction. So since, as we discussed, the cell size of the Li Fi network is very small, it is very difficult to have the frequent handovers. So prediction based algorithms are suggested in standalone Li Fi networks to handle the handover processes. Handover decisions are also taken on the basis of load balancing. So it can be possible that in a multiple access point scenario, most of the users are connected to one access point while the neighboring access points are sitting idle. So in that case, the load balancing schemes are used so that proper resources can be utilized. There are two types of handovers that are discussed in literature. One is horizontal handover. The handover happens from one Li Fi access point to another Li Fi access point, and in vertical handover, we use some heterogeneous networks like Li Fi plus Wi Fi, and the handover happens from a Li Fi access point to a Wi Fi access point. So in horizontal handovers, most of the prediction based algorithms are suggested to take the handover decision. For anticipation, we must know the exact location of the user or maybe the traffic profile. Arshad et al. Suggested to use topology aware handover skipping method. So we can understand handover skipping from these diagrams. Let us say the user 1 was traveling along this blue path. If we take the decision on the basis of received signal strength, the user need to go through so many handovers. However, if we use handover skipping, the signal power is compromised. So in this case, although we are receiving a high signal strength from this access point, the algorithms are used so that we can skip the handover, and also the user is having full coverage during its path. So this handover skipping was further explored on the basis of prediction and received signal strength. During initial research, it was realized that it is very difficult to work with a standalone VLC network. Therefore, the researchers introduced the concept of heterogeneous networks of using the Li Fi along with Wi-Fi. In that, it was suggested to connect all the users that are facing a blockage, low data rate, or are mobile must be connected directly to the RF access point. So, however, there is still a problem. It may be possible that almost 50-60% of the users in a network are facing such problems. However, we should not be connecting all the users to the Wi-Fi, because in that case, the Li Fi resources are not utilized properly. However, Wi-Fi is overburdened. So this problem was further taken up by many other researchers in the form of optimization problem. The optimization could be done on the basis of few parameters. Some researchers consider resource fairness and system utilization. The optimization problem was further explored whether we need a centralized controller or a distributed system to take the handover decisions, which one performs better and produces a highest system utilization. Furthermore, to achieve better system utilization, evolutionary game theory, fuzzy logic based or bandit theory based handover decision processes were also suggested. We implemented basic media access controller on software as well as simple implementation on the hardware. We'll be discussing those two in the further slides. So for software implementation, we used Riverbed Modeler and Omnet++. The Riverbed software is a commercial simulation software for simulating networks. It has paid licenses. It has antenna module that we needed in our system, and the packet formats are pretty easy. We can describe a packet by drag and drop method. It also supports wireless channel by using these transmitter and receiver module. There are inbuilt traffic generators. Queuing modules are used for describing MAC layer. So here the MAC layer is further described using a state diagram. This model also provides integrated mobility. The static collection is again easy. It supports various type of networks like voice over IP, TCP, LTE, WLAN, IoT, IPv6 and many more, but it doesn't support Li Fi and VLC. Also, it has limited literature and support because it is a commercial software. We also implemented on Omnet++. Omnet++ is open source software. It is available freely. However, there is no antenna modeling and the implementation is very tricky. You need to code here everything. But Omnet provides an extensive graphical user interface. Graphical user interface of Omnet Plus is much better than Riverbed Modeler, which was earlier known as Omnet. Also, Omnet Plus has wide online community support. So whenever you are stuck, you can always look up online. But for our simulation model, we needed to create a medium just to provide the range of the access points and the users. We also reused the mobility module, which is already available in open source implementations. We also implemented media access controller on a very simple hardware. The hardware we considered is very minimalistic that can be reproduced in any research institute. Now I will be briefing a Li Fi link. Let us consider our transmitter is connected to internet through a Ethernet cable. On the Ethernet cable, we will be getting Ethernet frames. The Ethernet frames, we must remove the Phi and MAC layer of the Ethernet and introduce our own Phi and MAC layer of the Li Fi link and send it directly as a baseband signal. The baseband signal is optionally added with a DC bias signal in case the signal is bipolar, and then it is sent directly on the LED. Note that the signal here is a positive signal because we cannot send negative signal to LEDs. And optics or lens is optionally used at the transmitter end to shape the transmitter pattern. The signal is then sent in the form of intensity, which is received by a photodetector. Concentrator is required at the receiver side to concentrate the signal at the photodetector. The photodetector receives the signal in the form of intensity variations and convert the signal in the form of current. The current is then converted to voltage using trans-impedance amplifier, and other amplifier stages are used to amplify the signal, and the signal is then sent to digital signal processing, and the headers are again inserted to send the Ethernet frame back to the device. Light communication is considered secure because it doesn't pass through walls. It is also energy efficient as light can be used for both illumination and communication. It is also safe because there is no adverse effect of light on the humans. Also, light communication can be used in radio frequency sensitive environments like airplanes and hospitals. So this is the basic hardware front end that we designed. On the right side of the slide, we present the top view, bottom view of the chips that we designed and a final packaged product. In our Li Fi transmitter front end, we used a very basic circuit. Here, our circuit can receive only unipolar NRZ signal. The signal is then given to buffer circuit to avoid loading effects. On the figure A, we can see the buffer stage, and the power supply is required to provide power supply to the buffer. The signal is then directly sent to the LED, which is displayed on the bottom view of the same chip, and the LED light then passes through the lens, which we can see in the Li Fi transmitter front end. For Li Fi receiver front end, we also used two stages. One is photo detection and then the amplification stage. The concentrator is required to focus the light on the photo detector, as we can see in the Li Fi receiver front end. And just behind this lens, the photo detector lies that we can see in the bottom view. The signal is given to transimpedance amplifier and other amplification stages, which we can see on the top view. And the power supply is required to provide power to the amplifier. Now our front ends were ready. These are the front ends that we just described in the hardware side. The idea was how to connect them to the software. How can we pass the data through this front end? For that, we used Python environment as it is very easy to implement. And for the Phi layer, we used universal asynchronous transceiver circuit because it can work on lower data rates. And our hardware front end was providing output in few Mbps. So our Python application was running in two systems. One was acting as transmitter and another was acting as a receiver. So we had some data and we divided it into smaller pieces, and then we inserted headers. The header contained the information of the packet length and the destination. Also, we added data padding to mitigate the flicker, and this data is directly sent to USB to UART, and the UART signal was provided directly to the NRZ end of the buffer at the transmitter side. And at the receiver, opposite processing is done as that of the transmitter. The USB sends the data to the computer, and at the programming end, we understand the packets by using the headers and where padding is removed, and then we further remove the headers and we process the data to display in our application. In the next slide, we will be displaying how our link was working in the hardware setup.
This is a Li Fi link setup. We are streaming video from transmitter to receiver over the visible light. This setup is working over a line of sight communication link, and therefore any obstruction in the communication path will corrupt the received data. For example, if we place an obstacle between the Li Fi link, received data will be corrupted. If we remove the obstacle, link will start working again.
With this, we are concluding our talk. So in the talk, we discussed about state-of-the-art research activities ongoing in media access controller of the Li Fi. Basically, we focused more on media access and handover processes. So for simulation, we have implemented media access control algorithms of IEEE 802.15.7 in OpenNet Modeler. We have also implemented a basic medium access control in OmNet++ for simulation purposes. We then presented a minimalistic hardware model for designing Li Fi frontend. And then we also introduced how we can use the design frontend and how can we use it to perform communication between two computers using UART and Python programming. This simple model can be used to perform analysis of different type of medium access controllers on Li Fi networks. We close the talk with future research topics. As we discussed, the VLC, that is IEEE 802.15.7, is developed from 802.15.4. So we can really look how it can be integrated to IoT devices, and the upper layers are already developed for 802.15.4. How can we integrate our VLC standard with those layers? This can really be a research topic, and for that we also need to know whether VLC devices are really energy efficient so that they can perform the functions of sensor nodes and IoT functions. Also, Li Fi is being standardized in comparison to Wi-Fi. So major mark functions and even some of the physical functions stays the same to push the commercialization. In this process, we are missing few things. First and foremost thing, the Wi-Fi MAC may not be efficient for Li Fi. So as we saw, CRMA based, that was central controller based control techniques, can be used to maximize the throughput of a Li Fi access point. So this can be further explored in the medium access controller. Also, coordinated multi-point communication or beamforming can further be explored for handover processing. So COMP was introduced in 4G to deal with the problem of interference. So this can similarly be used in Li Fi networks, as we are using same frequencies at the neighboring access points. We also like to point out that most of the research that is going on is performed on the simulation and most of the work is theoretical. So there is a lot of work that is required on the hardware side. What exactly can be used in the final model? Rigorous hardware implementation and research is required on that side. Also, some intelligent networking schemes are required so that we can use the network resources intelligently in a network. So it is also suggested to look in multi-point transmission control protocol so that we can avoid the vertical handovers in this using MPTCP. We can get parallel transmission from multiple technologies and this is how we can converge the network. These are the references. Thank you.
Thanks to all for listening to the lecture. Utkarsh, are there any questions?
Yes. So the first question is, have you implemented / installed the Li Fi hardware anywhere and like tried efficiency?
Again, please, the hardware is, I just displayed in the presentation that we use the Li Fi front end for Mac. I could not get the question.
All right. It was like it's about the implementation. Like people can see it right now. Is it like fully working or is it accessible to normal people?
Okay, right now for the Mac, we have not integrated it to the internet. So we have not implemented the, so we are using our own application layer and the Mac layer is developed on the Python environment. So we can do the changes there, but it is not connected to the internet.
All right. Next question is, why OFDM is proposed for Li Fi and not VNC? VLC, a visible light communication.
Okay, so in as in the earlier in the slides, so 802.15.7 is developed from 802.15.4. So the idea was to develop a low power, low data rate, and application for the devices that are very cheap. So the major thing was to support the personal area networks at that time. So the VLC standard was developed for, so the was again to provide indoor applications, but not for very high data rate. So that's why the idea of Li Fi is taken up differently, so that the high data rate applications can be handled. So for VLC, the idea stayed the same. So the modulation schemes stayed very less complex. So OOK and BPPM were suggested.
All right. Next question is, what was the order of latency introduced to Python packet processing?
So okay, so yes, there was a lot of latency. So we tried to introduce padding. Padding was fine. So we tried introducing some other things, but they created a lot of latency in current our implementation. There is no such latency at all because we are just in the link that we displayed. It shows a broadcast information. So just propagation delays there.
All right. Next question is, you have a lot of Chinese references. Do you get complete data / know how from those references? Like, is it the complete data?
Actually, I don't know how to answer this question. I just read the research papers. So the research papers don't actually give everything in detail. So that always stays a problem. So we have to implement in our own way. things we have to imagine what could have been done. So everything is not provided in the research paper.
All right. We have a follow-up question to that packet latency in Python packet processing. But the packet processing would introduce some latency, right?
Yes, so we didn't check that latency exactly. So really, so we did try to introduce some other processing techniques that were creating a lot of latency. So we left that to the FPGA part. So for our Python part, it was not creating much problem. So we didn't really look into that. What is the exact latency in the process?
All right. Any other question, chat? I don't think so. So thank you so much for your words, Miss Anjali.
Thank you so much, Utkarsh. Thank you so much to all.
All right. So we have reached the break of our session. We'll continue after 2 p.m. So let's take a short break and everybody relax, turn off your screens and join back us at 2 p.m. All right.
Kash, maybe for 15 minutes or sorry, as
Let's
per the
ask the chat.
slide, 1 hour
Chats, do
20,
you want a short
15
break or a
minutes.
long break? You can like put this suggestion in your question box.
I think 1 hour break is sufficient. Maybe 12, 23, 25 maybe. So 125.
125.
Are there any? Is there any concern? Then okay. Otherwise, I think so.
I got one suggestion. 2 p.m. is fine. One says long break. So let's do it 1:30.
I think this is good. Yeah, 132.
All right. So
Utkarsh, Dr. Arun have suggestion. We
yes.
can go as per the schedule.
All right. So there's no problem in like 2 p.m. It's a long break, but let's stick with the schedule then. I'll change the slide back up. Let's meet at 2 p.m. All right. See you, chat, at 2 p.m. Bye.
Can you change initial also? 12:25 now. Yeah, thank you.
And we are back. I hope you all had a nice break. I'm your host Utkarsh Kumar Singh, and with staff and research scholars working under guidance of Professor Abhishek Dixit, I'd like to begin the video demonstration part of this webinar. Let me formally introduce myself to you first. I'm Utkarsh Kumar Singh, project scientist at IIT Delhi. I was awarded Exemplary Student Award in my bachelor's in electronics and communication, and my research area includes graphene-based sensor designing and origami-based structure robotics. So here's my video demonstration. Hello, I'm Utkarsh Kumar Singh from Department of Electrical Engineering, Photonics Lab, Bharati School, IIT Delhi. And today, I'm here to present optical design of wide-angle constant focus lens and electronics assembly for visible light communication. So let's begin. This slide represents the end result of our project. That is, a system consisting of multiple light sources and providing internet connectivity to all the mobile devices below. We could easily compare this communication to any other communication architecture, such as, say, microwave communication, where multiple light sources act as base stations and mobile devices with microwave antenna could easily be replaced with mobile devices with Li Fi receiver. So here comes our problem statement. We need to have a constant focus for our mobile device visible light communication to work. Let's take this point up with an example. We have a light source here emitting paraxial rays onto a single spherical ideal lens that focuses on a single point where a photodiode is placed, and it converts the light signal into electrical signal so our communication could happen. But let's say, what if the orientation of the mobile devices changes or the light source moves? So in this case, if our photodiode was placed here and our focus is displaced here, our communication would stop. So we need to have a constant focus where our photodiode is placed. We need to solve this. So we are approaching this problem in two ways basically. First is the electronics and mechanical approach. Second, designing an optical system. So that's an optical approach. And third, the hybrid of both. And we'll also talk about optical MEMS for our future upgrade options. So let's take up the electronic system first. This is our example we talked about in earlier slides. We have a light source, lens, and a photodiode is placed here. For simplicity's sake, let's put our lens and photodiode into a single assembly, and let's call it a Li Fi sensor. When a light source is here, a light Fi sensor is pointing onto that light source so our communication could work. When the orientation of the sensor changes, the focus shifts. We have to manually realign this sensor to this light source now. So there comes the use of pan and tilt assemblies. Pan assembly provides movement in horizontal direction, tilt assembly provides movement in vertical direction. And with the combination, we could map out the 3D space around us and point our Li Fi sensor wherever we want. All right, to automate this whole process of pointing and tracking, we first made our algo, and we're using a microcontroller executing it with the camera module to providing the whole system with computer vision with assembly of pan and tilt servos. As you can see, the system is flawlessly able to track our light source, and this is our positioning data. As I go right, it goes right. As I go left, it goes left. So here's now working demo of our concept. This is our receiver circuit. We have a lens and a camera module. As you can see, it maintains a constant focus. Future upgrades to our electronics system. First, we're trying to convert it into a smart sensor. So it'll be able to detect which light source got the Li Fi internet connectivity and which doesn't. and we are approaching this problem with internet detection parity bits embedded in our Li Fi protocol itself. Second, multi-input, multi-output systems with roaming. And finally, we're trying to reduce the whole assembly site so it could be packaged into one single mobile device. So now let's talk about our optical approach. In the first approach, we packaged the whole system and moved it mechanically to maintain a constant focus. What if we could come up with such system or lens that maintains a constant focus even though when the light source or the mobile device orientation is changed? To discuss this further, we first need to take up the different types of light sources. You must have seen many different kinds of light sources releasing different kinds of beam, be it converging beams, diverging beams, or paraxial parallel rays. But in case of an actual LED, as you can see here, we simulated a real test bench LED. As you can see, it does not have a well-defined wavefront, and we need to focus such light beams onto a photodiode for maximum power transfer. This slide contains the step to how to create an optical system in COMSOL Multiphysics. That's the software we'll be using for this demonstration. So first, we make our geometry. It could be spherical, aspheric surfaces, waveguides, anything. Then you assign boundary condition to your geometry. In third step, you select the material or apply the gradient refractive index functions to your material. Then we talked about in earlier slides, you have to specify the ray release function. So you specify the ray release function or put an LED model for actual simulation results. Build a mesh around the whole system for computation, then run the study, analyze your result, then optimize. All right, so let's take it up with an example. As you can see, this is our lens geometry. Also, we have to specify the geometry of the imaging plane and any other optical component we like to put. Then we have to also specify the ray release, as you can see, and then if we run our simulation, this lens focuses on a single area that provide maximum power transfer and equivalent illumination in this area. So here are some simulation parameters. We are placing the lens 1 meter apart from the light source, and other light sources are also 1 meter apart from the center. To help you understand the results of our simulation better, I'll be comparing the simulation result of a normal basic spherical lens and our design aspheric lens. So as you can see, this is a normal ideal spherical lens, and here is our design. The first surface is a spheric surface, and the second surface is also a spheric surface but with hyperbolic gradients, and it also has a gradient refractive index function embedded into its material, and we also try to implement a parabolic concentrator here. Here's a 2D view of my 3D simulation to help you visualize the result better. As you can see, when the light is released from 3 different sources in a spherical lens, we have 3 different focuses. Or as we can say, if our light source moves from one place to another, our focus is also displaced. But as you can see, in this case, light falling from all direction is converted into a beam, and that beam could be further manipulated with the help of parabolic concentrators to convert it into a small point area focus. The spot diagram represents the same thing. As you can see, we have a center focus and multiple focuses on the imaging plane, but in this case we have an area of equivalent illumination, and we're trying to further optimize its performance so we could have maximum power transfer. Once our lens design is completed and our lens is fabricated, we could combine our electronics and optical approach. This will include our lens, photodiode assembly, and a panel assembly with a camera. Combining this, we'll get an optical electrical system that automatically focuses on a single point And even if the orientation of the device is changed, it keeps you connected to the Li Fi network. The whole system would somewhat look like this. Once we have completed our hybrid approach containing both electrical and optical part, we could start working on reducing the whole package's size and creating an optical microelectrical mechanical system containing lens, actuators, and a housing small enough to fit in handheld devices such as mobile phones. This summarizes the session. Thank you for your time and patience. All right. Hello. Are there any questions? I think there are no questions. So let's move on to the next part. Our next demo is by Vaibhav Singh. He has done his master's in power electronics and drives from Galgotia University. He is currently working as a senior project scientist at IIT Delhi.
Good afternoon to all the participants. Myself Vaibhav Singh, and I am going to present this demo. So in this session I am going to present the optical front end of Li Fi downlink, and I will also demonstrate the optical front end of Li Fi downlink on the hardware setup, that is transmitting any signal through the LED and receiving that signal at the photo detector. So here are some contents which is required for the optical front end of Li Fi downlink. I will show the whole block diagram of optical front end of Li Fi downlink, which will cover transmitter, LED, blue filter and optical lens, photodetector, receiver, and some calculated experimental results. At last I will show the demo on the hardware setup. In this slide, I am showing the whole block diagram of optical front end of the Li Fi downlink. As you can see at the transmitter, I am using function generator, bias T and DC power supply for driving the LED, which is converting electrical signal into optical signal. After the LED drive, the spread light is focused on pin photodiode with the help of optical lens. I am using pin photodiode for converting optical signal into electrical signal. Here I am also using blue filter at the receiver for passing only blue light which have a fast response and blocking the yellow component which have a slow response. After that, the electrical signal is passing through the three stages of the receiver circuit, which are the transimpedance amplifier circuit, high pass filter and equalization circuit. And at last oscilloscope will show the signal which is transmitted by the transmitter. So whatever signal is transmitted by the transmitter, receiver circuit will receive that signal and that signal will see on the oscilloscope. Let's discuss in detail all the parameters. First is transmitter. In the transmitter, function generator is using as a source and DC power supply is using for giving a proper offset. And the third one is VAST, which is a 3-terminal device where the first terminal is RF port which is connected to the function generator and the second terminal is DC port which is connected to the DC power supply. And the third terminal is RF plus DC port, that is the output of the VAST which is given to the LED. You can see in this block diagram. Here, this is the RF port of the BAST, this is the DC port of the BAST, and this is the RF plus DC port of the BAST, which is given to the LED. Coming to the next slide, which is for LED. So currently I am using one LED, which is a white LED, the combination of blue light and yellow phosphor component. So this LED is converting electrical signal into optical signal. And the minimum requirement for driving the LED, that is, the forward voltage should be minimum 2.7 volt and the forward current should be minimum 50 milliampere. Here the operating temperature range for the LED is also defined. Next is blue filter. Blue filter is using for filtering out the slow yellow component and passing only blue light, because the modulation bandwidth of the yellow phosphor component is typically 3 to 5 MHz due to the long response time, which also limits the bandwidth of the LED. Here the transmittivity of the blue light is 90% between 400 nanometer to 500 nanometer. After the blue filter, I am using optical lens in front of pin photodiode, which is a plano-convex lens. Here the size of the lens is 30 mm and the focal length of the lens is 25 mm. Now the optical signal which is coming from the LED will convert into the current signal with the help of photodiode. Here I am using SI pin photodiode, which has the cutoff frequency is 300 MHz and the photosensitivity of the photodiode is 0.2 ampere per watt at 440 nanometer. That is, we will get only 20% of the full light on the photodiode. After that we have receiver circuit. In the receiver circuit there are three stages. The first stage is transimpedance amplifier circuit, which will convert the current signal into the voltage signal. The op-amp I am using in the transimpedance amplifier circuit is OPA 847 and the gain bandwidth product of this op-amp is 3.9 GHz. Here the transimpedance gain of the transimpedance amplifier circuit is 12 kilo ohm. Since the photo current is generated by the photodiode is in the range of microampere, so I take the value of the gain of the transimpedance amplifier circuit is in the range of kilo ohm, and the calculated value of the feedback capacitor is 0.25 picofarad. The second stage is high pass filter, which is for filtering out 50 Hz power frequency signal and reducing the low frequency noise. Here the cutoff frequency of the high pass filter is 289 Hz. And the third stage is equalization circuit, which is a passive equalizer circuit. This circuit has been designed to enhance the bandwidth of the Vlc system. Now here are the some calculated experimental results, that is, first is transmitted communication power, which is 20 milliwatt or 13 dBm, and the second is receiver sensitivity, which is 0.1 milliwatt or minus 10 dBm. Both the calculation, that is the value of the transmitted communication power and receiver sensitivity, is measured by the light meter. And the third is the distance between LED and photodiode, which is 30 centimeter. Here I am also showing the overall 3 dB bandwidth of the VLC link. So when I am not using the blue filter, then the 3 dB bandwidth of the VLC link is 2.5 MHz. And when I am using the blue filter, then the overall 3 dB bandwidth of the VLC link is 12 MHz. And when I am using the blue filter with the equalization circuit, then the overall 3 dB bandwidth of the VLC link is extended to 20 MHz. So the achievement of the 3 dB bandwidth of the VLC link is shown in demo. In this demo, I will show the optical front end of Li Fi downlink by transferring an analog signal between LED and photodetector at higher frequency. which is currently 20 MHz.
Now I am demonstrating the Li Fi downlink by transferring an analog signal between LED and photodetector at higher frequency, and I will show the impact of blue filter, that is how blue filter will help to enhance the bandwidth of the VLC link. So as I am shown in the PowerPoint presentation, here I am using function generator as a source and now taking an analog signal, that is a sine signal with the amplitude of 1 volt peak to peak. This signal is going to the RF port of the bias T through the cable, and I am giving the offset from this power supply to the DC port of the bias T through the cable, and the output of the bias T, that is RF plus DC port, is giving to the LED. Here I am using only one LED, so I am giving the offset of 2.8 volt and it drawn 80 milliamp current. Now the LED is on, that is it is converting electrical signal into optical signal. Now this optical signal is converting into current signal with the help of fin photodiode. After this, the first stage of the receiver circuit is converting current signal into voltage signal, which is known as transimpedance amplifier. Now that voltage signal is passing through high pass filter circuit and equalization circuit and receiving that signal on this oscilloscope. Now you can see the received signal. If I block the path between LED and photodetector, then we will not get any signal on this oscilloscope, and if I remove my hand, we will get the signal on this oscilloscope. Here this link is receiving the signal without using blue filter. So let's check the overall bandwidth of the link. Here we can see the amplitude of the signal is 416 millivolt peak to peak at 100 kilohertz. Now for calculating the 3 dB bandwidth, first we will see at which frequency the amplitude of the signal is getting 290 millivolt peak to peak. So that frequency will be the bandwidth of the link. Now I am increasing the frequency, that is 200 kilohertz, and the amplitude of the signal is 420. Now again I am increasing the frequency, that is 500 kilohertz, and the amplitude of the signal is nearly 416 millivolt. Again I am increasing the frequency, that is 1 megahertz. The amplitude of the signal is 400 millivolt. Now again at 2 megahertz, the amplitude of the signal is 316 millivolt. Now at 2.5 megahertz, the amplitude of the signal is nearly 283. So that frequency is the 3 dB bandwidth of the link, that is 2.5 megahertz without blue filter. Now I'm using the blue filter between LED and photodetector. So you can see after using the blue filter, the amplitude of the signal is reduced because of the photosensitivity of the photodiode. which is 0.2 ampere per watt at 440 nanometer. Again, you can see if I plot the path between LED and photodetector, then we will not get any signal on the oscilloscope. And if I remove my hand, then we will get this signal again on the oscilloscope. Again, let's check the bandwidth of the link when using blue filter. Here we can see the amplitude of the signal is nearly 50 millivolt peak to peak at 100 kilohertz. Plus, now for calculating the 3 dB bandwidth, first we will see at which frequency the amplitude of the signal is getting 35 millivolt peak to peak, which is the 0.7 value of the 50 millivolt peak to peak. So that frequency will be the 3 dB bandwidth of the link. Now I am increasing the frequency, which is at 500 kilohertz. The amplitude of the signal is remains same. Again increasing the frequency, that is at 1 megahertz. The amplitude of the signal is again same. Now it's 3 megahertz. The amplitude of the signal is same at 5 megahertz. The amplitude of the signal is nearly 45 millivolt. Again I am increasing the frequency again at 10 megahertz. The amplitude of the signal is nearly 40 millivolt. Again I am increasing the frequency at 15 megahertz. The amplitude of the signal is now 37 millivolt. And at 18 megahertz is again nearly 37 millivolt peak to peak, and at 20 megahertz I am getting 35 millivolt peak to peak. Again I am increasing the frequency, that is at 20 megahertz, 22 megahertz. The amplitude of the signal is now 30 millivolt. So at 20 megahertz we get 35 millivolt peak to peak. So this is the overall 3 dB bandwidth of the link using blue filter. As you saw the demo, the achievement of the overall 3 dB bandwidth of the VLC link is 20 MHz with the communication distance between LED and photodiode is 30 cm. Here I am used only one LED, that is, the longer distance could be achieved if more identical LEDs were used. Thank you.
That was a great demo, Weber. Now, I'd like to please turn on your camera and please address the questions by the chat. You're not audible, Weber. Can you please check your microphone? We cannot hear you, Vaibhav. No, I cannot hear you, Vaibhav. Can you please like disconnect and reconnect your microphone?
Hello.
Yes, you are audible now.
Okay.
Are the questions visible to you by the chat?
Yes.
All right. Please like place a microphone near your mouth. Your voice is too low.
Okay. Okay. Am I audible?
Yes.
Okay. Okay. The first question is, what is the effect on communication system if avalanche diode is used, photodiode is used? Is it better than pin photodiode, and what are their effects on different noise like short thermal etc? Okay. So I worked on only pin photodiode, so I have not compared with the avalanche photodiode. Okay, so I don't have any idea.
All right. Let's move on to the next question.
Okay, so second is, just for the information, what is the collection efficiency on the of the link? Okay. Yet I have not calculated it. Third one is, can we simulate it through Opti system software? Uh, I have not simulated the design in the Opti system, so I don't have any idea. I worked only hardware setup and go through theoretically. How much improvement is there in bandwidth with and without equalizer? Okay, so equalizer I have used is a pre-emphasis circuit. So first calculated the transfer function of the equalizer circuit, which is more than 20 megahertz. And when we add to that the link circuit, it improves the bandwidth of the system. Okay, so no more question.
I guess there are no more questions from the chat. I'd like to thank you, Vaibhav.
Okay, thank you, Utkarsh.
Yes. Vaibhav, please kindly turn off your webcam. All right. Next demo is presented by Mr. Ankit Kumar and Krishndeep Gupta. Mr. Ankit has done his master's in technology in electronics and communication from National Institute of Technology, Srinagar, and Krishndeep Gupta has done his master's in technology in electronic circuits and system design from Aligarh Muslim University. Their demonstration is on VLC design in FPGA.
Very good afternoon to all the participants. Myself Ankit Kumar, and I am going to present this demo with my colleague Krishndeep Gupta. So we are going to present the VLC implementation using FPGA. First of all, I want to discuss the motivation behind using the FPGA in the VLC implementation. What are the advantages of the FPGA? So, since visible light communication requires implementation of higher order modulation schemes to enhance the bandwidth, so there are we can extend the bandwidth of visible light communication by using the high front ends up to a certain bandwidth. After that, we need to implement these modulation schemes, and since FPGAs are widely known for their high performance and throughput, so we have implemented the these modulation schemes over the FPGA, and that's why implementation of VLC in a FPGA has improved the data rates. And FPGA also work concurrently. If I compare the FPGA with the normal microcontroller and microprocessors, so those are the sequential devices, and FPGA work concurrently, and FPGAs are also very good at doing the fast digital signal processing. So that is the reason we have chosen FPGAs to implement VLC. So here on FPGA, basically we are implementing physical layer and MAC layer, which are the two key part of implementing VLC in FPGA. So in this demo we are going to talk about the physical layer. So this is the block diagram which we have implemented in the FPGA to implement the modulation scheme. So here we have used a QAM4 modulation scheme uh, for the enhance the bandwidth of our VLC system. So first of all, we will take a data that is a random data that we can take from any source. In our case, we have taken it from a PRBS generator, and then that data is going for a symbol mapping, QAM4 symbol mapping. Before that, we will also do the signal serial to parallel conversion, means we will convert the serial data into 2-bit parallel data, and after that, that 2-bit parallel data will get converted into the constellation points. Means let's say if we are having 0 0, then according to that we will assign some value to y, and we will assign some value to q, and we will generate our I and q data. After that we will implement a pulse shaping filter. So this pulse shaping filter with band limit our channel. So whatever bandwidth that is available on our Li Fi link, so according to that it will band limit our signal. So and basically the bandwidth that we get after the pulse shaping filter is given by a simple formula of 1 plus alpha divided by 2t, where alpha is the roll of factor and t is the symbol duration. So we will here pulse shape our signal. So we have used here root raised cosine pulse here. So the next would be interpolation. So we require interpolation since to the sampling rate of our DAC and the sampling rate of our signal is different. So we need to match the sampling rate of our DAC with the signal. So interpolation will do that work, and after that we will combine our I and Q data by in the band pass modulation. So we will generate the cos and sine signal, and then we will multiply the cos signal with I data and sine with the Q data, and we will generate a final transmitting signal I cos omega t minus Q sine omega t, and that signal we will pass to the DAC. And so this is our transmitter part, and after that that data will go to the channel or Li Fi link, and after that at the receiver side we will again receive that data by using the ADC, and after the ADC we will again demodulate our signal. Means we have done a band pass modulation by using a carrier. We will again demodulate our signal, and we will change our signal from pass band to base band. And after that next would be the decimation. Since we have done the interpolation at the transmitter, so we will do the decimation at the receiver by the same factor by which we have done the interpolation at the transmitter. After that the next block would be match filtering. So the match filtering, we have the uh, same coefficient as of pulse shaping filter. Those are the complex conjugate coefficient are the complex conjugate of pulse shaping filter, and next would be symbol synchronization part, that would tell us the right sampling point where we should sample our received signal. And parallelly we also need to do the carrier recovery here. So after this we will do the detection, or we will take a hard decision over the signal, and then we will do a symbol demapping, and after that we will our symbols get converted into the bits, and whatever signal we have transmitted from the transmitter we will able to recover our signal back. So as you can see, from data that we have transmitted till the DAC, that is our transmitter part, then there is the channel, and after that from ADC to the point where we have again generated our bits, that is our receiver part. So this is the whole block diagram which we have implemented over the FPGA. So this is our experiment setup, which is showing the FPGA board which we have used, and also the ADC and DAC board. So inside this FPGA board, as we can see, this would be the connectors. So basically these are called as P mode connectors, where we will give our normal random data as an input to our system, and after the data will go inside the FPGA, it will get passed through all these transmitter chain, from symbol mapping, pulse shaping, interpolation, band pass modulation, and after that data will reach to this DAC board. So this is the Abaco FMC 150 ADC and DAC board. So this board is having both ADC and DAC. So this board is having two channels which are 16-bit resolution, and ADC is also two channel with 14-bit resolution, and this DAC ADC board is connected with this FPGA board by using a FMC connector, as we can see here. So this board is having two FMC connector, and with one FMC connector this board is connected, this ADC and DAC board is connected with our zinc board. So now the process would be, we will give the input from here, it will get passed through all the transmitter blocks, then it will go to the DAC, and the DAC will convert it into analog output. That analog output will go to the Li Fi transmitter, or it will reach to the LED, where the signal will get converted from a electrical signal into the light, and then after passing through free space it will reach to the Li Fi receiver, where there will be a photo detector, and again our light will get converted into electrical signals, or more specifically analog signal. That analog input will reach to the ADC, and the ADC convert the analog data into the digital data, and the data which we have again received will get passed through all these blocks, and we would be able to receive our original bits which we have transmitted at the transmitter. So this is our experiment setup that we have done. So next we are going to show some demos. So our first demo is about the implementation of modulation scheme over the FPGA. So in this demo we have implemented the transmitter part over the FPGA, and we have verified it. We are going to show the demo of QAM implementation in the FPGA board. So we are implementing the 4 QAM modulation scheme inside the FPGA. So here we will send the random data to the PRBS, from the PRBS to the FPGA, then we will pass it to the DAC, and then we will see the result. So here this is the PRBS, that is pseudo random binary sequence generator. So from this PRBS we are generating a 7.6875 Mbps signal. Now this signal is going to the FPGA. So this is the Zinc Ultra Scale Plus FPGA, and this is the our ADC and DAC board. So the input signal is going inside the FPGA through the P mode. This is a P mode connector, and then after going inside the FPGA, so as I have already shown or discussed in my block diagram, it will get passed through all these blocks. So once it get inside the FPGA, so first of all it will get converted from serial to parallel. Conversion will happen, and after that the QAM4 symbol mapping would happen. There our bits will get converted into the symbol, and we will be generating the INQ data. Then according to our channel bandwidth which we are having in the VLC, so according to that channel bandwidth we will pass our data through a pulse shaping filter, where we have used the raised cosine pulse. We will do the band limit, we will band limit over the signal. So after the pulse shaping, then since now till now our signal will be with the lower sampling rate, and we have to match our signal with the sampling rate of the DAC. So currently our DAC is working on the sampling rate of, this DAC is working on a sampling rate of 61 MSPS. So we have to upsample, or we have to interpolate the signal. So we will use the interpolation filter to interpolate the signal, and after doing the interpolation, we are having I and Q data. So we will, by using a sine and cos signal, we will combine our I and cos data. So our overall final transmitted signal would be I cos omega t minus Q sine omega t. That will be we will transmit after through the DAC. So now we will transmit this, our final transmitted signal, through the DAC, and since we have passed it through the DAC, so we can see here that after the modulation, so the random signal which we have sent through the PRBS, this is the our received signal after the DAC. So now, since to check how to check whether we are getting the correct signal or not, so for in the QAM4, if we send a simple clock signal instead of the random signal, so according to equation, our equation would be like some constant and then cos omega t minus sine omega t. So the signal should look like a sine wave. So now we will transmit the clock signal instead of random data, and then we will see whether after the DAC we are getting the correct signal or not. So as we can see here, we have transmitted a clock signal of the same rate through the PRBS, and we are able to get the sine wave after the DAC. So this shows that we have correctly implemented the transmitter part of the QAM modulation scheme over the FPGA. So in the next demo, we are going to demonstrate the interfacing of FMC 150 ADC and DAC board with the FPGA board. In this demo, we are going to show how we can convert the data between analog to digital and digital to analog domain.
So in this demo, we are demonstrating the interfacing of ADC, DAC with the FPGA board. So in which we are giving the analog input from the from the function generator to the ADC, and getting back analog output through DAC and seeing on the DS. So we are giving the analog input around 15 MHz sine wave signal, which have a 1 volt peak to peak and 500 millivolt offset. So this analog signal is coming giving to this cable to the ADC. This ADC is a 14-bit ADC, which is the sampling rate of 250 MSPS, and it is going to the FPGA via FMC connector, and then loop back to this input which is coming to the function generator. It is the input of DAC channel, one DAC channel, and this in this FMC card there is a two two channel DAC, which is 16-bit, and it has 800 MSPS sampling rate. So this signal coming to the input of a DAC, and then output of the DAC is the analog signal, which is a sine wave of 15 megahertz, which will giving to the ADC as input via function generator. And now we are getting a same sine wave which is 15 megahertz, around 15 megahertz, and we receiving a signal strength around 900 millivolt. So what we are giving 1 volt peak to peak, but we are getting around 900 millivolt. There are some attenuation also. Now we are when we are changing the frequency like 1500 to 17 megahertz and 920 megahertz, 21 megahertz. Now in the real time we can see that the frequency also change at the same time. So but it has limitation. It can be sampled up to 55 megahertz, as you see. Now we are sending a square wave signal to the ADC, and from the and seeing on the other end of the DAC output, we are getting a square wave signal. We giving a 2 megahertz square wave pulse, 1 volt peak to peak, and now we are getting a 2 megahertz 1 volt peak to peak square wave pulse. So in this way we are interfacing our FMC card, which have ADC and DAC. We are interfacing this card with our FPGA. We are giving an analog signal, and we are getting back the analog signal.
Thank you.
All right. I guess we have a question in the chat. Mr. Ankit Kumar and
Yeah.
please address that.
Yeah. So Anvesh Shisu has asked that what is the roll of factor value that we have used in the pulse shaping filter. So we have used a value of 0.4 as a roll of factor in our pulse shaping filter. So as I can see, only one question is there, Utkarsh.
Yeah. Any other questions, chat?
There is another
Thank you,
question
Mr. Ankit
for
and Krishna.
Vaibhav.
Thank you.
Yes, I've already sent it to Vaibhav. He'll like answer that in the chat only. All right. So let's move on to the next part. Next demo is presented by Dr. Arun Goyal. He's the principal research scientist in electrical department, IIT Delhi, and his research area includes signal processing, sensor array processing, sonar imaging, comprehensive sensing, and optical communication. And his demonstration is described in VLC in USRP.
Good afternoon, all of you. Welcome to the webinar on Indigenous Li Fi 5G testbed at IIT Delhi. I am Dr. Arun Goyal, working in the Li Fi project in the principal project scientist at Electrical Department IIT Delhi. I am here to present a demo on the physical layer of the simplex Li Fi link that we have developed in our lab. So before discussing the demo, I will give you the brief background of this demo. That will include the introduction about the block diagram of the physical layer of the Li Fi link, the source that we have used, in the demo, and the symbol mapping. This symbol mapping will depend on the types of the modulation scheme we have used. I'll also provide you the software and hardware details that we have used in this demo. So this is the typical block diagram of the physical layer of a simplex Li-Fi link. Generally, in any communication system, there are three major components: transmitter, receiver, and channel. So this is a transmitter, this is a receiver, and this is a channel. In transmitter, the source will generate the digital data in the form of bits, and these bits are mapped into the symbol depending on the modulation scheme we have used. And in order to avoid the inter-symbol interference, pulse shaping is used. For this demo, we have used root raised cosine filter as a pulse shaping filter. The output of the pulse shaping filter is a complex IQ data or the baseband signal, which is modulated onto the carrier with the help of this USRP. So the USRP will generate the passband signal, which when passed through the channel and received by the other USRP at the receiver end. Now coming to the channel, in case of Li-Fi link, the channel is a wireless channel that will include the front-end circuit at the transmitter as well as receiver. In front-end circuit at the transmitter, LED circuit is used, and at receiver, photodetector circuit is used. So the signal generated, passband signal generated by the USRP will be transmitted via the LED and received by the photodetector circuit at the receiver end. Since this front end is the separate demo that is demonstrated by other member of our group, I have not used this front end circuit in this demo. I have used a wired channel for the communication link. The output of the received USRP will then undergo from the passband to the baseband, and this baseband signal will undergo match filtering as well as timing synchronization. The received signal obtained at the after timing synchronization will contain some phase of the frequency offset. So in order to compensate for the phase offset, carrier recovery circuit is used. Then the symbol will be estimated from this received signal and mapped into the bits. This symbol to bit mapping will be reversal to the bit to symbol mapping we have used at the transmitter. The source that can be used as a transmitter will be either text, audio, or video. For this demonstration, we have used text source. The text test TEST ... is used, and this text is converted into a digital data using the ASCII code. The bits obtained will be then mapped into the symbol using bit to symbol mapping, and this will depend on the modulation technique, digital modulation technique. In case of BPSK, there are two symbols, so one bit is required. So the bit B0 will either 0 or 1. So the bit B0 will be mapped to -1, and the bit B1 will be mapped to +1. In QPSK modulation scheme, there are 4 possible symbols. So 2 bits are required to map all the 4 possible symbols from bit to symbol. So we have bit B0, which have the same mapping as the BPSK, and bit B1 will have the same mapping as bit B0. So by using all the I and Q combinations, we can obtain all the 4 bit to symbol combinations. In case of QAM, there are 16 bit to symbol mapping combinations are possible. So 4 bits are required to map all the possible bit combination to the symbol combinations. So we can think of 16 QAM as a combination of 2 4 PAM along I and Q channel. So each 4 PAM can be represented with the help of 2 bits, and there are 4 possible symbol combinations. This is shown in this table. So 00 is mapped to -3, 01 is mapped to -1, 11 is mapped to 1, and 10 is mapped to 3. Similarly, for Q channel, we have the bit to symbol combination. Then by using I and Q combination, we can obtain all 16 bit to symbol combination for QAM 16. Now all the constellation does not have the unity power. So to normalize the power, we use a normalization factor. In case of BPSK, this normalization factor is 1. In case of QPSK, it is 1 by root 2. And in QAM, it is 1 upon root 10. So for this demo, we have used two USRP X310, one for transmitter, another for receiver. Each USRP X310 is equipped with UBX 160 data board. Each USRP is connected to the host computer with the help of a 1 gigabit Ethernet SFP module, which supports up to 25 megasample per second. We have used open source toolchain GNU Radio Companion 3.8.2.0 as a software for baseband processing. In the figure, I have shown the architecture of the UBX 160 data board. I want to emphasize that all the processing will be done in the baseband, and this data board will take IQ data in the baseband and then modulate into the passband with the help of this mixer. Hello everyone, welcome to the Photonics lab of IIT Delhi. I am here to present the demo of the physical layer of the Li Fi link that we have developed in our lab using USRP X310. So this is a setup. So we are using two USRP. This is one of the USRP that is used as a transmitter, and it is connected to the host computer. This is another USRP, second USRP that is connected to the host computer. This USRP will act as a receiver. Both the USRP are connected with a wired channel. We are not showing here the LED in the photodetector circuit, that is the front end circuit, because this is part of our another demo. So we are using the GNU Radio open source toolchain, in which we have designed the BPSK modulation scheme. This is the script of the BPSK modulation scheme. For this demonstration purpose, we have choose sample per symbols equal to 4 and the carrier frequency is equal to 10 megahertz. So that will give the full bandwidth of 2.5 megahertz. For the roll-off factor of 0.35, the calculation of the bandwidth gives 1.6 megahertz. So I'll start the simulation. So this is a transmitted waveform of the BPSK signal, and this is before modulation on the carrier, that is in the baseband, and this is the spectrum of this signal. And here it is shown the bandwidth is equivalent. The bandwidth is around 2 megahertz in the baseband, and which is roughly equivalent to 1.6 megahertz. And this is the constellation diagram of the BPSK scheme. Now I'll move to the receiver. So I'll turn on the receiver, start the simulation. So this is the constellation diagram of the received signal after the demodulation. There is some frequency offset with the constellation points in the blue, and this will be taken care by the carrier recovery circuit, and then the constellation will become steady. These are the received waveforms of the demodulated signal in the baseband at the receiver, and this is the respective spectrum of the received signal. Now I'll show you the text data. I'm not using the packet communication, so there is an ambiguity to decide from where the text start. So this will be taken care manually, and there is a phase ambiguity of 180 degree. So this is a desired text test dot dot. So we will receive the text correctly, and now I'll move to the next modulation scheme, that is a QPSK. So in the QPSK also we use the same parameters, that the carrier frequency is 10 megahertz, sample per symbol equal to 4 sample per symbol is equal to 4. Therefore we have the same bandwidth but different constellation diagram. So this is the transmitted waveform in case of the QPSK modulation scheme before it is modulated onto the carrier, and this is the spectrum. Here also the spectrum has a bandwidth of roughly around 2 megahertz, and this is the constellation diagram of the QPSK. Now I'll move to the receiver. So I'll start the QPSK receiver. I'll zoom in, and the points on the blue is rotated in the constellation diagram due to the frequency offset, and in the red these are compensated after the carrier and the phase of carrier recovery circuit, and these are the received waveforms of the QPSK modulation scheme, and this is the respective spectrum. Now I'll show you the text. So there will be a phase ambiguity of 90. So now I'll receive the text correctly in the QPSK scheme. In the BPSK modulation, we achieve the data rate up to 2.5 Mbps, and in the QPSK case, the data rate will become double, that is 5 Mbps. Thank you.
All right. Do you have some questions, chat? I don't think so. So thank you so much, Dr. Arun Goyal. Our next demo is presented by Mayank Gautam. He received his Bachelor's of Technology degree in Electronics and Communication Engineering from GTS IPU, and he's currently working as Project Associate at IIT Delhi. His demonstration is on VLC uplink.
Hello participants, I am Mayank Gautam and I am going to present a demonstration on VLC uplink based on RF frequency. In this presentation, I will be covering these points, which includes basic information about VLC uplink followed by the design implementation goals and solutions. I will also discuss the overview of VLC uplink design followed by some demonstration videos. Now, let me provide a brief overview of VLC uplink. So, using VLC communication system, one can transmit video, voice and data just like any other communication system using visible light spectrum, but only in one direction, that is downlink. Therefore, in order to provide bidirectional data transfer in a VLC communication system, VLC uplink is implemented, which can be developed using RF or IR technology. Here, I am going to present the VLC uplink implementation using RF technology. Before going towards the design implementation, let me talk about some of the challenges, or I should say requirements we need to fulfill. First of them is high data rate. The design should be able to transmit and receive data at higher speeds. Along with that, the communication should be reliable at all time and at longer distances also. Next is the compatibility. The design should be compatible with all the hardware used in this project. Let me give you an example. In the Li Fi project, we are using ZCU102 board as the main component around which our entire project will work. So the design should be implemented in such a way that every component used by the VLC uplink is made compatible with the ZCU102 board. Next up is the ease of integration. The VLC uplink design needs to be flexible enough so that it can easily integrate with other parts of the Li Fi network projects. To explain this, let's consider VLC uplink access to the Li Fi MAC layer. The MAC layer needs an easy integration with the VLC uplink design in order to transmit and receive packets over the link. This brings us to the fourth point, which is usability of the design. The implementation should be able to provide easy to use interface, something like an abstraction layer in form of an API to simplify the usage of the design. Now, let's move towards some of the solutions accepted in order to achieve the desired goals. For ensuring high data rate of the link, PCI Express protocol is selected as the interface between the RF frontend and the ZCU102 board. Talking about the compatibility of the PCI protocol with the ZCU102 board, the ZCU102 board offers a high-speed PCI route port Gen 2 4 lanes which can be used by the RF frontend. The RF frontend is also a PCIe 2-lane supported dual-band module which works at 2.4 GHz and 5 GHz frequency spectrum. The RF frontend module also supports on-chip OFDM and QAM256 modulation technology. Now, both the devices which are ZCU102 board and the RF frontend module are interface compatible with each other, which is the PCIe interface. But in order to make this work, a custom kernel is developed which helps the two devices to communicate with each other. The custom kernel is developed over a fork of Xilinx kernel repository which is provided by the Xilinx for ZCU102 board. Also, a custom software platform is developed to provide a simple user experience and ensure ease of integration with other parts of the project. The software platform works as a middleware between the kernel and the user application, which will be presented in this demonstration. This block diagram shows the architecture of the VLC uplink design implementation. The communication between the ZCU102 board will be handled by the RF front-end module, which act as a physical layer device for the VLC uplink. The front-end module and the processor system, also known as PS part of the ZCU102 board, are interfaced using the PCIe slot available on the ZCU102 board. The PCIe driver for the RF front-end module is incorporated in the custom kernel of the operating system. The driver is responsible for providing the basic application programming interface for the RF front-end module. The application programming interface provides handler for controlling and configuring the front-end module. The custom kernel also provides an interface for accessing the driver functions from the Linux user space. On booting the ZCU102 board, the custom kernel will load the PCIe drivers and creates an interface at the Linux user space, which acts as an endpoint for communicating with the RF frontend module. The application is developed for the Linux platform and runs on the Linux user space as the user application. The application provides a command line user interface for controlling and communicating with the front-end module. To summarize, the VLC uplink design comprises of three major components: a Linux user application for the users to control and communicate with the link interface, a custom kernel which provides the link interface between the user application and the PCIe driver. The PCIe driver, as the name suggests, drives the RF frontend module, which is the physical layer device of the VLC uplink. This ends the basic explanation of the RF-based VLC uplink design implementation. Now, let's move forward towards the demonstration of the VLC uplink. The VLC uplink demonstration is developed using these components, which includes a ZCU102 Zinc Ultrascale MPSoC development board, which is a high-performance hexa-core processor coupled with a Xilinx 60nm programmable logic fabric. The ZCU102 board is interfaced with a dual-band 2.4 GHz and 5 GHz supported RF front-end module. This demo also requires a SD card prepared with the necessary files required to boot and run the demo on the ZCU102 board. The boot files, which includes basic ZCU102 board files, a custom kernel, and user application. All these files are developed using Xilinx provided Linux software development kit, also known as Linux tools. This setup consists of two identical parts as you can see here. Talking about the individual parts, each part includes a ZC102 development board with which the RF front-end module is connected via PCIe port. A SD card is inserted in the SD card slot of the ZC102 board. This SD card is preloaded with the entire software stack developed for the demonstration, which includes Linux operating system, custom kernel, and the user application programs. The ZC102 board is also equipped with a monitor connected via DisplayPort to provide output from the operating system and a keyboard to take input to the operating system. The keyboard is connected to the USB Type B port using an USB adapter. The other part of the setup is connected in the same manner as the part I have just explained. This summarizes the hardware setup overview. Now, in order to work with the setup, we need to configure the software part also. First, we need to start the server on the first board, which will start advertising itself to the other board, so that the other device can establish a connection with the server in order to communicate with each other. The software is easy to use and operate the desired functionality of the device using the command line interface. So, all the commands that are programmed can be viewed by using this command. All the commands are displayed and explained on the console window. Now, to start the connection server, this command is used. This command requires some mandatory arguments which are server name to which the device will request connection to and a code which authenticates the connection request. In our case, I will be using uplink as the server name and 1234567890 as the code for authenticating the connection request. The command will start the advertisement server and also assign an unique ID to the device, which will reference to the board for sending and receiving data on the link. As you can see, the program will show the ID allotted to the server board. Now, once the advertisement server is started, we can connect the other board to the server using this command. This command also requires some mandatory arguments which are server name to connect to and the authentication key which is set on the server board. After successful connection, the board is allotted with a unique ID for board reference, which is 250. With this, the setup is configured to communicate with each other. Coming to the demonstrations, our first demonstration is to test the data rate of the link. To overview this demo, we are going to start a testing server on board 1 and connect this server from board 2. To clarify this, test server is different from the advertisement server we created earlier. This server runs on port 5201. After that, software will start transmitting a random data for an interval of 10 seconds, and after each second, it will calculate and displays the data rate the link is operating at. Let's see it in action. As the link is already connected and both the devices are allotted a board ID, we are going to use this command on board 1 with ID 159 to start the test server. This requires no argument. Now the server is started at port 5201. Now on the second board, we are going to start the test using this command. Note this command requires an argument which specifies the board ID of the board with which we are going to perform the test, which is in our case is 159. Now the random data transmission is started and after 1 second interval, data rate is calculated and displayed on the screen. At the end, At the end of the transmission, the average speed is calculated and displayed, which comes out to be around 100 Mbps. To verify, the receiver speed is displayed at the server side also. To summarize, what we have done here is first we connected two boards with each other, then started a test server on board 1 and acquires a board ID to reference it to the board. On board 2, we started the test by providing the board ID of the board we need to perform the test with. The testing program transmits a random data, calculates the data rate, and displays it in our console window. Next up is the test transfer demonstration. In this demonstration, the first step is to connect the two boards and acquire the board IDs. The process has been already discussed in previous slides. After that, the text receiver application is started on board 1 and on board 2, text transmitter application will be started. Now, on the text transmitter application which is running on board 2, the type text is transmitted to the receiver application on board 1. The receiver application on board 1 displayed the text on the console window. Let's see it in action. Here both devices are connected with each other and board IDs are allotted to both the boards. Now on board 1, this command will be used to start the text receiver program, which will wait for the text reception from the other devices. Once the data is received, it will be displayed here. Now on the second board, we will use this command to start the text transmission program. The command requires the board ID of the board we are transmitting the data to. Now type the text followed by the enter key to transmit it. Let's say we type hello world and send it. Here the text received and displayed on the first board. Let's try another text string. Say this is Li Fi demo and send it to the board 1. This is the text transfer demo. To summarize what we have done here, first we connected the two boards, acquires board ID. On board 1 started the text receiver program and on board 2 started the text transmission program. After that, on board 2, we type the text and transmits it. This brings us to the last demonstration, which is video transfer demonstration. The process is similar, which follows connection of two boards and board ID acquisition. Next up, on board 1, a video stream is started, which will be playbacked on the other device using the VLC uplink. The process of streaming the video includes creation of RTPS server and using the server to stream the desired video file. The video playback is executed by providing the board ID of the device on which the stream is transmitting. Let's jump onto the demo. So here the boards are connected and board IDs are assigned. Now the board 1 with ID 159, we will use this command. This command is used to start the stream and it requires the path of the video file to transmit. The SD card connected on the ZC102 board includes a text video file in MP4 format on the file system, which we are passing to the program in order to transmit it. Now the program is starting a RTPS server and parallelly playing the transmitted frames. Now on the receiver side, we will be starting the playback using the video receiver program. The command also requires the board ID of the transmitter. Now, the receiver program will start playing the received video frames. As you can see, the transmitted frames are lagging behind the received frames. This is happening due to the fact that video transmitter program is playing the video frames after transmitting them. On the other hand, the receiver program is playing the video frames as soon as it receives the frame. Now, let me stop the transmission of the video file. The receiver program stops playing the frames as it no longer receives any data. Now, let me stop the receiver playback and notice the receiver program enters a looping condition which retries receiving the data from the same transmitter, but it fails to do so as we stop the transmitter program, which also stops the RTPS server. Now, if I restart the video transmission, the receiver starts receiving the video frames again and plays them on the display. The video file we are transmitting is a full HD video which requires a high data rate in order to be played without delay and without any frame skips. The video transmission program transmits the video in looping mode, means it never stops transmitting until we manually stops it. The board ID allotment is used in order to connect multiple receivers, which helps isolating and distinguishing between the devices during the reception and transmission of the data. To summarize the video data transmission demonstration, the process includes connection of two devices followed by the acquisition of unique board IDs, after which on board 1 a RTPS server and video transmission is started. On the second board, the video receiving is started from the transmitter and a video playback is shown on the monitor. That's all for the VLC uplink demonstration. Thank you.
All right. Mike, could you please address the questions in the chat and turn
Okay,
on?
I have answered the question in the chat box only.
All right. Chat, are there any other questions? No? So let's begin the next session.
Thank you.
Now, Rakesh and Sharifa are here to demonstrate MAC protocol in FPGA. They're both working on MAC protocol on VLC as project scientists at IIT Delhi.
I am Sharifa Fairoz, project scientist. I'm going to present on my work on PSPL interfacing and PL design for data with conversion. This is the Li Fi network. From PC, that video data is sending via Ethernet to the processing system of Zing SoC and processing system to programmable logic interfacing using AXI protocol. Then programmable logic data is sending to Li Fi link and data is received back to the programmable logic. Then programmable logic to processing system interfacing using AXI protocol and processing system to PC data is sending through Ethernet. In this processing system to programmable logic, my work is processing system to programmable logic interfacing using AXI protocol and PDPL design for data with conversion from 32 to 1 bit at the transmitter side and the receiver side data with conversion from 1 to 32 bit and the PL to PS interfacing using AXI protocol. PSPL interfacing design. In this, processor and DDR memory controller are contained within the Zinc PS side. Then XI DMA and PL design are contained within the Zinc PL side. And XI Light bus allows processor to communicate with the DMA to set up, monitor, and initiate the data transfer. Then AXI MM2S and AXI S2MM are memory mapped AXI4 buses that allows DMA to access the DDR memory. Then access MM2S and access S2MM are AXI4 stream data buses. They are used for continuous streaming of data without addresses. They use between DMA and PL side design. PL design at the transmitter side. This is PL design is for data with conversion. In this blue colored blocks are the IP cores that used in the PL side. First, after AXI DMA, data is given to AXI for stream before. It is used for clock domain crossing from 100 MHz to 7.68 MHz. Then AXI for stream data with converter. It is used for converting 32-bit wide AXI for stream data to 8-bit wide AXI for stream data. It is given to FIFO generator. This will convert 8-bit wide data into 1-bit wide serial data and is used for buffering. PL design at the receiver side. Serial data is getting at the 7.68 MHz at the receiver, and we are giving it to the FIFO generator code. This will convert this 1-bit serial data into 8-bit wide data. Then it is given to AXI for stream data with converter. It will convert 8-bit wide data into 32-bit wide AXI for stream data, and then it is given to AXI for stream data before. It is used for clock domain crossing from 7.68 to 100 MHz and is used also for buffering. And it is given to AXI DMA. This grey color is the PS side. This and this is SOC and DDR4. This is the simulation result. First signal is the 100 MHz clock, and in this clock, this signal is working, and this is the counter data. It is given as the input to the AXI4 stream data before. Then it is given to a stream data with converter, and its output is given to FIFO generator, and the FIFO generator output is the 1-bit serial data at the 7.6 MHz. This fourth signal is the serial data. This signal, the third signal is the 7.68 MHz clock signal, and at that frequency we are getting the serial data output. And this fifth one is the output 32-bit wide data output at the second FIFO generator. FIFO means data stream FIFO at the receiver side. And actually this signal is running at 100 MHz clock, but there are a lot of idle clock cycles due to which at the receiver side we are getting 1-bit at the 7.68 MHz only, and DMA need 32-bit wide data at 100 MHz clock. That's why there are a lot of idle clock cycles, and simulation output is getting as expected, and this complete design with RS along with PSPL interfacing is run on the code, and text data is transferring, but for video data subprogram, that is output data received at the memory is not playing correctly, and I am working on that.
Good afternoon, all the participants. Myself, Rakesh Kumar Reddy Oraganti. I am working as a senior project scientist in IIT Delhi. Here, in the topic, I am explaining about the data communication between PS to PL and PL to PS. PS means is a processor section, and PL means is a programmable section. This data communication is we are implemented in the FPGA. This is the block diagram which we have implemented for the data communication between one PC to another PC through ZCO102 board and Li Fi link. Here in ZCO102 have two sessions, one is PS and one is the PL. PS means is a processor section. Here you are using for the processor, and here we are using for the programmable logic design. This programmable logic design is already explained by the Sharifa in the previous presentation. In this presentation, I am explaining about the data communication between PC to PS using Ethernet protocol and PS to PL using AXA protocol in the transmitter side. And also on the receiver side, I am explaining about the data communication between PL to PS using AXA protocol and PS to PC using Ethernet protocol. How we can transfer the data through Ethernet protocol and AXA protocol, I am explaining the next slide. Here I am explaining about the Ethernet protocol. Ethernet protocol is used for the interfacing between PC to PS and PS to PC. And next I am explaining about the programming flow of execution between transmitter side and receiver side. First I am explaining about the transmitter side. Socket here PC work as a client and PS work as a server. First I am explaining about the client at the PC. First socket function is used for the creating the TCP/IP socket. Here connection function, new connection we can create for the client in the client side, and the send function is send the data transfer from one send the data transfer to Ethernet client to the server. Next, I am explaining about the server programming. Socket function is used to create the TCP/IP socket here. Bind function is used for the binding the socket and server address at that function. Listen function is used for the here the socket server in the passive mode, where it will wait for the client to approach the server to make a connection. Here wait for the client connection until to make a connection. Next accept function is here connection is established between client and the server. After connection is establishing, the receiver function is receiving the data from here. Here after connection establishing, the data transfer the data received it successfully and sending the properly also. Here the make whole the data transfer communication between client and server. Here I am explaining about the receiver side. Receiver side we are reverse processing doing here. Reverse processing means here PS is work as a client and PC work as a server. I am explaining about the client at PS side. Socket is creating the TCP/IP socket here, and connection newly connection is created from the client. Send function is used for the sending the data from client to server. And another side I am explaining server side. I am explaining socket is created for the TCP/IP socket. Bind connection is used for the bind the socket and server address. Listen here, wait for the client request. Here wait for the client and accept if connection is established. Here accept function is used for the connection is established between client and server here in the accept function. After accepted function is completed, the data transfer from sender to receiver is properly. This is the whole Ethernet protocol work here properly. Here I am explaining about the AXA protocol. AXA protocol is used for the interface between PS to PL and PL to PS. And next I am explaining the programming flow of execution between transmitter side and receiver side. First I am explaining about the transmitter side. Transmitter side, the data received at the PS. After that, the interfacing between PS and AXI DMA used for the AXI light, and here the data received AXI light. After that, AXI DMA, and finally we give it to the PL. In AXI DMA, why you are using for the MM2S here? MM2S means memory map to stream conversion. This is used for the data transfer from DDR memory to the FPGA. This memory used for that one. That's why we are using AXI DMA memory map to stream conversion. Same I'm doing in the receiver side also. Here the data flow is PL to AXI DMA and AXI light. After that the PS. Here AXI DMA used for the stream to memory map protocol. Here the stream to memory map protocol, why you are using the data transfer from FPGA to DDR memory. We are using for the stream to memory map you can use here. The AXI light used for the interfacing between the AXI DMA and PS. That's why we can use the receive the data here. This is the whole process works on the AXI protocol. In this demo, I am explaining the data transfer between PC to ZC102 and loop back to the PC. In this demo, we are explaining about the data transfer between PC to FPGA board and looping back to the PC. Through Ethernet protocol, I am explaining about here. And also we are in ZC102 board. Here also the internal loop backing I am working here. In internal loop backing PS to PL and loop backing to the PS. Here we are working on the protocol on AXA protocol. After AXA protocol, here we are working on. To achieve these results, we developed an application. We developed an application through Linux platform using Xilinx Metalinux tools. After this application is developed here, and we are running here the Xilinx ZC102 Metalinux tools here working here, and this OS we are booting through SD card boot mode. After that we are running the application here in the ZC102. Here in ZC102, after OS is coming, we are running here the server application. Server application we are running here. Here the server is waiting for the client request. If we are running the client application in PC. Here we are running the client application. After we are running the client application, the data transfer between the data is transferring from PC to ZC102 and again loop back into coming in the PC. This is the data transferring right now. It is doing here. Here in the data transferring, here we are receiving the how many bytes at a time we are sending the data from PC and receiving the data at PC. Here we are showing the data here. Here we are running the very fast, that's why it is not displaying properly. After completing this, I will show this one. After this is the data transmitting is going on here right now. After completing the data transmission, here the output video is coming here and input video is coming here. This one is the input video and this one is output video. We are displaying here and showing to the output here. This one is the input video and this one is output video. In previously here the receiving bytes of data here 1024 and at a time we are receiving the data. After receiving the whole bytes of data here total bytes we are received here and sending to the total received here. Thank you.
Thank you, Rakesh and Shaifa, for your well-demonstrated session. Chat, do we have any questions for them?
No, I didn't get any questions.
Yeah. So I guess this is the end of the webinar. It was great having you all. I'd like to conclude this webinar on Indigenous Li Fi 5G testbed, and I'd like to thank you everyone for your time and patience. Stay home, stay safe.